Okay, so they need me to do.
Not now. I was sorry. I was trying to. Okay, now which one? Oh, this one. Okay, sounds good.
So maybe if you could just go back to sharing your screen again, just for the intro.
I've never been, but I've heard. Yes.
I think it's not looking. And second, you know.
So many questions. So,
Yeah, sometimes we just.
Very good chair.
It's not changed. I'm seeing back.
I'll do this like kind of
And
use the eye.
People eye, just chairs.
Or.
Yes.
I think the only thing that you'll have to do now is when I started using the step forward.
Oh, I didn't know.
It's okay.
Oh, do you want to, so we said after the session or?
I made that for kind of at the end of our session. Jump to that, but Yeah,
Okay, yeah.
the main thing is.
And also, I think what we could do for Q&A is just have this one
Oh, yeah, if we need it,
if I need it.
yeah. I'll let you keep the judge of that, okay?
Okay.
Yeah.
It started as the usual marking data except on. But now it's sitting with the transformer. Now.
Oh, she could have come yesterday. I just had 2 meetings.
She just showed
Yeah.
application.
Well, my wife works last year. Usually
Hello, everybody. Welcome to day 2. We're about to get started. My name's Cameron. I'm helping organize. So yeah, just a quick rundown of the morning. So there's food over here. If you leave to get food, please don't come back through this door, even though it's unlocked. Yeah, so we have the poster session after 2 great talks. So definitely please attend that and see as much as you can. That's downstairs. You walked past it when you came in. Our first talk is going to be from Melanie Weber, who's an assistant professor of applied mathematics and computer science at Harvard. She runs the geometric machine learning group. Previously, she was a Hook Research Fellow in the Math Institute of Oxford and has a PhD in applied math from Princeton. And then after that, we have a contributed talk. So short session this morning, and then the posters, lunch, and come back for afternoon session. Maybe you can jump ahead to that as well. Cheng, you just step ahead one more. Yeah, so in the afternoon, we have 2 invited talks. I didn't prepare intros for those, but you can see them. Yeah, so please stick around. So yeah, Melanie, come on up.
Perfect. Yes, thank you very much for the introduction and to the organizers for having me. Is this loud enough, or should I use some microphone?
This one is.
It's on, it's right. Okay. Okay.
This one's just for the room.
Okay. Hopefully, if you can't hear me, let me know. Yes, so my talk will be today on discrete curvature and applications in graph machine learning. So some quite different topics than what we've seen yesterday. Before we talk about graph machine learning, I just want to start with sort of more generally my research area and where graph machine learning falls into that. So my work is generally on geometric machine learning. And geometric machine learning, as I approach it, sort of has 2 ingredients to it. The first one is data geometry. So we want to understand what kind of structure we have in data and models that might be useful for downstream learning tasks, and then find good parameterizations of that geometric structure. And then the second piece to that is, once we have an idea of what kind of structure we find, we want to design methods and algorithms that can make use of that structure, ideally to learn more efficiently, or maybe to have better theoretical guarantees on those algorithms. And I'm particularly interested in problems where the data is graph-structured or where the data lies on a manifold. In this talk, of course, we will focus on the first part, where the data lies, where the data is graph-structured. So graph machine learning. The talk will be fairly theoretical and methods focused, but before we get into that, I want to give you an idea of what the kinds of learning problems are that we encounter in this space. So in graph machine learning, there are a couple sort of standard tasks that we often encounter that we can ask about graph-structured data. One such example is graph classification. So in graph classification, our input is usually a set of attributed graphs. And we want to assign labels to those graphs. So we want to classify the set of graphs. One classical example here that you can think of from biochemistry is where each of those graphs represents the chemical structure of the molecule. And then we want to predict the property of those molecules, such as toxicity, or maybe how effective a molecule would be if we build it in a drug. Another example is node classification or community detection. Here, our input is a single graph, such as a social network, for instance, and then we want to assign labels to each node in the graph. So in the social network example, maybe the nodes are users, and we want to predict whether or not a given user is human or whether it's a bot. And then the third example that you see down here is link prediction. Here again, the input is a single graph. We have a few edges given, and we want to predict additional edges in the graph. So one classical example where this appears is in truck discovery, where each of the nodes represents a truck. And then maybe from experimental data and public health data, we know some adverse reactions between those trucks. So we need a few edges. We already know a few edges, and we want to predict where other adverse reactions might occur. So those are a couple of classical graph machine learning tasks that you can sort of keep in the back of your mind as we go through algorithms for learning models to solve these tasks. And then the second term that you saw in the title was discrete curvature. So this will be the central geometric tool that we use in this talk. Curvature, I'm not sure how many of you have a differential geometry background. Even if you don't, you probably know that curvature is a really central concept in differential geometry that allows us to characterize global and local properties of geodesic spaces. Classically, it's defined in continuous settings, right? If you think of curvature, you might think of objects, surfaces like the ones that you see here. You might know, for instance, that the Euclidean plane that you see here in the first little cartoon, that is a flat space, so that has curvature 0. The sphere is positively curved, and then you might have encountered such saddle-like structures that would be an example of a negatively curved manifold. So this kind of intuition on what curvature means we usually associate with continuous spaces. But then it's also possible, and we will see some notions in the talk, to define analogous curvature notions in discrete spaces, such as graphs, for instance. And then again, those notions will allow us to characterize local and global properties of our data. And that kind of structural characterization we will see can be very helpful in graph machine learning. Let me give you a couple of examples of methods and algorithms that people have studied using these curvature concepts. And then for some of those, we will take a closer look. So probably the first algorithms where curvature was used were related to community detection. So that's a shallow graph machine learning task. There's no deep learning, no graph neural networks, and the task is usually done unsupervised. It's a very simple task. So as you see here on the right-hand side in the cartoon, in community detection, we typically assume that we have a graph that has some dense substructures that are sparsely connected, and we want to recover these dense substructures. And typically we assume that nodes that are in the same dense subgraph have some shared property that maybe correlates with the labels that we want to assign to those nodes in a node classification task. So that's community detection. It turns out that a good way to do community detection is to find these sparse connections between the subgraphs and cut them. And it turns out that curvature can be very useful in identifying those. So this is an observation that most of these algorithms rely on. There are also extensions of those algorithms if the situation is a bit more complicated, like you see in the second cartoon, where the communities are actually overlapping. So in both of those cases, the kind of geometric characterization that we get from curvature can be really helpful. Curvature can also be or is being used in deep learning on graphs, in graph neural networks. This is something that we will take a closer look at in this talk. In particular, while graph neural networks are really popular machine learning architectures and have been very successfully applied in many, many areas, there are some caveats, some challenges that arise. And it turns out that the geometric information that we get from curvature can help us mitigate some of those challenges. So this will be something that we will discuss at length in the talk. And then a third class of tasks where curvature is really helpful is when we actually want to understand something about the geometry of our data. So where we don't assume sort of beforehand that we have a geometric characterization, or maybe we don't have any domain knowledge that tells us what the geometry of the data is, and we want to learn a characterization in a data-driven way. It turns out that curvature then can also be really helpful to understand something about the geometry of the data manifold And then that also has implications for the design of machine learning algorithms. So we will talk a little bit about that at the end of the talk. Okay, so let me start with actually introducing some of those discrete notions of curvature that we have now mentioned. So as I said earlier, classically, curvature is defined in continuous spaces. It's unfortunately not possible to map those notions one-to-one directly to discrete structures, because in order to define curvature, we need differential structure. Like the curvature, which is characterized by this tensor that you see here, like really relies on having a differential structure. And then if we're in a discrete setting, we don't have a natural differential structure. What we can do instead is to use curvature analogies. So we can say that in the continuous setting, curvature is related to certain other properties that might have natural or well-studied analog in the discrete setting. And then we can define a curvature notion that preserves this relationship. And we will see two examples of how we can use such analogies to construct curvatures. The kind of curvature that we are focusing on here is Ricci curvature. So this is not the full curvature tensor that you see here, but basically only one component of this, which in particular characterizes local curvature. So the technical definition is probably beyond what we can go to in this talk. But what you can imagine about Ricci curvature is that like if you look at a point on a manifold and you look at the geodesic ball around it, and you want to understand how that ball grows, and that has nothing to do with the local curvature on the manifold, and that is roughly speaking what Ricci curvature measures in the continuous setting. Now in the discrete setting, the first curvature analogy that we want to look at was introduced or suggested by Ollivier. And that has something to do with the relationship between curvature and random walks on a manifold. Namely, in the continuous setting, we can show that if we start two random walks at close by points, then they will stay close together if the manifold, with high probability, if the manifold is locally positively curved. And if the manifold is negatively curved and sort of the space is expanding, then with high probability, the two random walks will draw apart. Random walks is something that we can easily study on graphs, and that's been done at length in the literature. So Ollivier suggested to take this well-studied field of random walks on graphs and define a notion of Ricci curvature on graphs that preserves this relationship. And we can do this as follows. So if we look at the cartoon here on the left-hand side, sorry, the right-hand side, let's say we start a random walk, a uniform random walk at the node U and the node V. Uniform random walk here means that it jumps with probability 1 over the degree to each of its neighbors. Right? Then we see that if the two nodes share a lot of common neighbors, then very likely the random walk will sort of stay close by and the random walks will explore each other's neighborhood. And then if there are not a lot of joint neighbors, then it's much more likely that the random walks will draw apart and will sort of proceed into the graph away from the two nodes. So this property can be measured with the Wasserstein-1 distance. So those two random walks induce a measure on the neighborhoods of each of those nodes. And then if we compute the optimal transport distance, the Wasserstein-1 distance between those two measures, then we see that that is high if there's not a lot of overlap between the two neighborhoods and the random walks draw apart. And it's going to be small whenever there is a lot of overlap between the neighborhoods and we don't need to transport a lot of mass between the neighborhoods. And then if we look at that equation here, d sub g, that's the shortest path distance on the graph. In our case here, that's just 1 because we look at adjacent nodes. And then we see that the curvature will be negative if the Wasserstein-1 distance is large, and it will be positive if the Wasserstein-1 distance is small. So in other words, this behavior of when we would expect the curvature to be positive or negative aligns with what we see in the continuous setting. Yes.
So can I just ask, so like, if you just take a continuous manifold and kind of discretize it to look like a graph and say, fine, like, will this converge back
This is the third part of the talk. We will get to that.
Oh.
Yeah. Great question. Any other questions? Okay. So this is our first curvature notion. The second curvature notion that I want to introduce was proposed by Forman. It derives from a completely different curvature analogy. Namely, in the continuous setting, there are some fundamental relations between Laplacians and Ricci curvature. And Laplacians are also well studied in the discrete setting, right? In graphs, for instance, we have the graph Laplacian, which there's a lot of work on this, and we understand the properties of the graph Laplacian really well. So this fundamental relationship between Laplacians and Ricci curvature in the continuous setting is the Bochner-Walzenberg equation, that is written up here. And then Forman said that we can define a curvature notion that preserves this identity with the discrete Laplacian in whatever combinatorial setting we are at. Most generally, that can be shown for CW complexes, which encompasses graphs, for instance. And then if we write down Forman's curvature for the case of an unweighted graph, so again, looking at this cartoon that we had previously on the other slide, that we get a notion like this. And you see here that that curvature notion has a lot of sort of combinatorial counts of like the degrees of the adjacent nodes, the number of triangles and quadrangles adjacent to the edge, and so forth. If we compare those two notions, so both of them are analogies to curvature in the continuous setting, right? There's some, and each of them preserve sort of some properties of the classical Ricci curvature that correspond to the properties in the continuous setting, but not all of them. We will get into continuum limits for the Ollivier curvature later on. What's also to note is, and that will be important for the applications that we will see shortly, is that Ollivier's curvature can be computed quite efficiently. Ollivier's curvature cannot be computed very efficiently because we have to solve an optimal transfer. So that has a cubic complexity. And if we try to compute that on a very large, very dense graph, there's some limitations. It's possible to compute an approximation to this that can also be work well in practice, but in general, computing Ollivier's curvature can be quite difficult. Forman's curvature just relies on this combinatorial information, so that's much faster to compute. Both curvatures, even though they come from very different curvature analogies, are somewhat consistent. So for instance, if we have high Ollivier curvature, we also have high Forman curvature. If we have low Ollivier curvature, we also have low Forman curvature. And one can in fact also show theoretical relations between those two notions. Okay. So now we know what discrete curvature notions are. Let's talk about how we can use them in the context of graph neural networks. So to remind you, I'm assuming probably most people have seen graph neural networks before, but let me remind you about graph neural networks, so sort of the basic structure of graph neural networks. So graph neural networks are usually used in a context where we have attributed graphs. So the graphs have a connectivity structure, right? We know which nodes are connected by edges, and then each node has some attributes, some feature vector associated with it. And then the graph neural network learns a joint representation of the connectivity structure and the features associated with each node. It has two components, an aggregation function and an update function. So in the beginning, we initialize those representations that the graph neural network learns with the attributes in the input graph. And then in each iteration, in each layer of the graph neural network, if you like, we update the representation of each node. And if we look at the node B, then we aggregate the feature information, the embeddings of the neighboring nodes into a multiset. And then we pass that through an aggregation function that computes some kind of statistic, summary statistic of this. So this can be an average, it can be an element-wise max. So there are some choices here on how to compute this aggregation function, but we get some aggregation of the information given in the neighborhood, and that is what we call the message. And then we pass that message through an update function together with the current representation of the node. And this update function is some trainable function, so you can implement it with an MLP, for instance. So this block of a message and then the update forms sort of one layer of the graph neural network. And then, of course, you can stack that on top of each other and get a deeper graph neural network. Okay, so what might go wrong? So before we talk about what can go wrong, in general, that's a great architecture that works really well for many of these graph structured tasks, including the 3 tasks that we saw earlier. In most settings, graph neural networks perform best on these kind of tasks, given the range of methods that we currently have available. But they're not without challenges. In particular, if we try to make, or as we make the networks deeper, we see some challenges arise. So for instance, we have here a cartoon that's sort of like an extreme case of a graph where we can nicely illustrate some of those failure modes, but you can also observe it in graphs that don't have exactly that extreme structure. The first potentially challenging effect that can arise is oversmoothing. So imagine we are updating, we are looking at the representations of one node in one of those dense regions that are colored here in red. Then you see that a node in the red region and its neighboring nodes share a lot of common neighbors. Right? So if you think about what this aggregation function computes in each layer, it kind of sees the same multisets and then computes some statistic, let's say an average over this, right? And if we do this for many, many layers, then we kind of smooth out the information that was originally given in the node attributes. So as we make the network deeper, it becomes harder and harder to distinguish nodes in those regions. So you can see if we perform a node classification task, for instance, how that can be harmful, how that sort of takes away important information that we would need in the downstream task. So this effect is called oversmoothing. And now if we bring in the curvature perspective and the geometric characterization that we can get from this, and then you can imagine that those are regions where we have positive curvature, right? There's a lot of, if we were to start random walks in these densely connected regions, right, the random walks would stay very close by. And this is, if we go through the steps of computing Ollivier's curvature, for instance, this would be regions where we have positive curvature. Now, the sort of opposite of that is oversquashing. That in our cartoon graph would appear along the blue edge mostly. So if you look at the nodes adjacent to the edge colored in blue, right, then this node over here only ever sees sort of a summary statistic of the information given in the other cluster in the graph, right? So through that edge, through the aggregation function, we only ever see like a very aggregated version of the information that's given in the other community in the graph. So if in our downstream task we really rely on capturing well information or correlations between nodes that are far apart in the graph, and then these kind of bottlenecks in the graph can be really harmful and can lead to information loss. So that effect is called oversquashing. And again, if we bring in this curvature characterization and this geometric perspective on the structure of the graph, then we see that occurs in regions of the graph that are negatively curved. This can be shown with respect to both of those curvature notions that we've seen before. So both Ollivier's curvature, also Forman's curvature, has this property that we have very low curvature in the graph where we would expect oversquashing and very high curvature where we would expect oversmoothing. So what can we do about those two effects? There are some model interventions that we can do. So we can make some changes in the message passing architecture that we introduced a few slides ago to mitigate effects such as oversmoothing. I want to mention here that Bobak Kiani is somewhere here, will present a poster later on, poster ID number 3. So if you want to learn about model interventions, please stop by that poster. What I will talk about here are not model interventions, but data preprocessing. So techniques that we can do, small modifications that we can do to the input graph to mitigate oversmoothing and oversquashing effects. without making any changes to the graph neural network's architecture itself. And how can we do this using curvature? So the general idea of this pre-processing technique called rewiring is to do edge perturbations. So in a sense, to add some edges where we have these bottlenecks in the graph and remove some edges where we have these very densely connected regions where oversmoothing occurs. Now we have to be very careful how we do these perturbations, right? We don't want to add and remove too many edges because otherwise we use crucial information that we need to perform well in the downstream task. It turns out that this characterization that I mentioned here only informally can be made much more precise in terms of connecting how much oversmoothing or squashing occurs in terms of curvature. And we can use this characterization to determine sort of what is too much oversmoothing and too much oversquashing, and use this curvature to guide how we perform those perturbations. In particular, by looking at the distribution of curvature across a graph, we can determine sort of thresholds for what is too low curvature and too high curvature, and then add edges wherever we think we have too low curvature and remove edges where we think we have too high curvature. This can again be implemented with both Forman and Ollivier's curvature. The results that I'm going to show you here are for Forman curvature. Again, Forman curvature might in this context be more preferable because it's much more scalable. And this is just a pre-processing technique, right? We still want to train the graph neural network afterwards. So we want to make this as fast as possible, this pre-processing routine. Importantly, what's nice about curvature-based rewiring is that there's not much hyperparameter tuning involved here because we can compute these thresholds for where we add and remove edges directly from the curvature of the graph. So this is not a parameter that we need to tune. We can really directly read that off from the curvature of the graph. And this is just one set of experiments to show you that this is actually something that works in practice. I don't have time to go through the theory here. We can also mathematically analyze the effect of curvature-based rewiring. But just to show you here some examples, so those are some biochemistry tasks. So this would fall in the category of graph classification that we discussed earlier. And here the graph neural network is a GCN, so a very classical message passing graph neural network. And then you have over here results for the performance of the GCN without any rewiring, without any pre-processing. In blue here, that's with Forman curvature. And then here are some other examples of rewiring techniques. And you see here that curvature does a good job, gets the highest values in most cases, and it doesn't require much hyperparameter tuning, whereas these other methods need to be fine-tuned.
A quick question.
Yeah.
So is there any way to think of kind of doing this dynamic rewiring as also just including higher powers of your adjacency matrix or something in your aggregation? Just I'm imagining like in the low curvature region, you could look a couple of steps, maybe you can go deeper kind of into the cluster or something.
That's interesting. Yeah, so curvature is usually really computed it's very local. It only takes information from the two-hop neighborhood into account because you compute it at an edge level, right? So you only look at like the adjacent nodes and their neighborhoods. You could look at more general notions of curvature that look sort of along a path in the network, but those become computationally much more expensive. So I don't think anybody has tried it, but it's a reasonable idea to try. Yeah. Any other questions? No. Okay. Then let me move on. So this is oversmoothing and oversquashing. So that has something to do with the sort of training dynamics of the graph neural network. Another potential challenge that arises in graph neural networks are limitations in the representational power. So we can ask, in the context of graph machine learning, we want to learn cross-structured functions, and we can ask what are the kinds of cross-structured functions that a graph neural network is able to learn, is able to represent. And unfortunately, graph neural networks have some severe limitations there. There are some even simple functions that a graph neural network is not able to learn. So in order to think about how we can study this question, one way to approach this is to look into what is called as graph isomorphism testing. So we can ask when a graph neural network is able to learn distinct representations of graphs that are not topologically identical. So basically, when can a graph neural network learn to distinguish two graphs that are not the same? And in particular, we have two graphs that are structurally very, very similar. Does that create failure modes of the graph neural network where it learns the same representation for two graphs that we would like to be able to distinguish in a downstream task? So what do I mean with topologically identical? So graphs in general are permutation, have a permutation symmetry, right? There's no natural order relation on the nodes of a graph. So in other words, if we take a graph's adjacency metrics and attributes, and we permute them, so we basically change the indices, then that shouldn't change, and that doesn't change anything about the topology of the graph. So if we take two graphs and we permute, and there's a way to permute the adjacency metrics and the attributes so that we get the adjacency metrics and the attributes of the second graph, then they're topologically identical. And the task of graph isomorphism testing asks to see whether or not for two graphs that are not identical, so for which we don't have such a permutation matrix P, whether we can tell that that is the case. So a classical, this problem has been studied well before graph neural networks. It's known to be very, very difficult. Like we don't have an efficient algorithm for this, but we have a relatively good heuristic that works well in general. So that works well on many classes of graphs, but that also has some failure modes. So this heuristic is the Weisfeiler-Lehmann test, and I want to illustrate how the test works and also at the same time illustrate a failure model. So here we have two simple graphs, G1 and G2. They're obviously not the same, right? If you look at certain graph characteristics here, G2 is not connected, G1 is connected. The largest cycle in G1 is 6, the largest cycle in G2 is 3, right? So obviously those two graphs are not the same. Now let's look at the Weisfeiler-Lehmann test, which is sort of the best heuristic that we have for graph isomorphism testing. So to initialize the Weisfeiler-Lehmann test, we assign some colors or some labels to the nodes. Here I just put a 2 because all of the nodes have degree 2, but we could also use colors or some other labels. And then what the Weisfeiler-Lehmann test does is something that's very similar to the aggregation function in the graph neural network. Namely, it looks at the labels of the neighbors at each node and then aggregates them in a multiset. So in this case here, I just labeled a few, right? We aggregate the labels of all neighbors. So we have a multiset of 2, 2 at each of the nodes. And then we perform a hash. We hash those multisets and sort of relabel relabel the nodes in the graph. In this case here, we would get the exact same multiset everywhere in the graph. So if we relabel this, we would assign the same label to each of the graphs, right? And then we could do another round of this aggregation. And we would see that we would always stay with the same labels, right? Each node has degree 2. So we are always aggregating the sort of local neighborhoods of each of those nodes look exactly the same. So we would always keep the same labels. So the Weisfeiler-Lehmann test in this case would output that G1 and G2 are the same, are isomorphic, even though they clearly aren't, right? So this is a common failure model, yeah.
Isn't that because the same label on the node as initialization?
Oh,
If you use that random numbers, does it?
If there are different attributes that would yeah, we're only looking at the connectivity structure here. Yes,
right.
if you have yes, if you have different attributes, right, then you have, if you think of our definition of topological identity, that also factors the features into account. Right, yes, so if we have different features, then that would be, yeah. So, but in terms of the connectivity structure, we can't distinguish those two graphs with the Westphal unit test.
On the like, I think. Because if you, always ask, if you go deeper, so as for initial number, if you go deeper in the graph,
Yes,
then you will see something different. So instead of 2, you may have.
we will get to that in a second. It's a good observation. Yes, yes. So if we just look at if we just aggregate this information over the one-hop neighborhood, as we do with graph neural networks, we cannot distinguish those two graphs. So this, in fact, doesn't only hold for those two regular graphs, but in fact for all regular graphs. And unfortunately, it also goes beyond regular graphs, two graphs that are more realistic. So another example where the Westphal test also fails, for instance, is this task on a biochemistry task, right? So those are two molecules. Obviously, we see that they are not the same, but they're very similar. And this would also be something where the Westphal test would learn exactly the same representation from these graphs. Now, why this Westphal test is important. So it was shown in two papers in 2019 that the representational power of the Westphal test is actually comparable to that of a message passing graph neural network, right? Because of the similarity of the aggregation function with how the Westphal test proceeds. So in other words, any two graphs that are not topologically identical, but that the Westphal test cannot distinguish, a message passing graph neural network would also learn the exact same representation form. And then one can also show the reverse. So there are message passing graph neural network architectures that one can construct that can distinguish all graphs that the Westphal test can distinguish. Okay, so we have this sort of equivalence, and we can basically use the Westphal test as a proxy for measuring what kinds of classes of functions a graph neural network can and cannot learn. Okay, so we have identified sort of some failure modes, some classes of graphs that a message passing graph neural network cannot learn. Now we already had a question from the audience: what if we take higher order structures into account? That in fact helps and extends the range of function classes that a graph neural network can learn, but it's also much more expensive to train, right? In fact, that's been proposed in this paper, Morris et al. It's called higher order message passing graph neural network, but it's not practical beyond like order 2 and maybe order 3 on smart graphs. So we need some other ideas for how to overcome this. And another idea is to, again, go the data preprocessing route rather than a model intervention route, and think about if we can augment the input graph with additional structure information that is hard to learn for the graph neural network. And this is an idea that's been around for a while. People have thought about various structure information that we can use to augment the graph. So for instance, the spectrum information about the spectrum of the graph Laplacian is a very good idea that can tell us things about whether the graph is connected, for instance, whether there's a community structure. Those are things that we can see in the spectrum of the graph Laplacian, for instance. And we could also look at counts of substructures. That is another common augmentation technique. Those kind of augmentations are called encodings. And usually what you do with that additional information is that you attach it to the node attributes or usually the node attributes, sometimes at the edge level, depending on where that information is given. You probably already guess where this is going. I'm going to suggest to use curvature for this, right? So we said earlier, I have already seen some examples where curvature gives us a characterization of the geometric structure of the graph. And perhaps that is helpful for the network to have. Also note that we had said earlier that curvature takes information in the 2-hop neighborhood into account, right? So that already gives us a hint that perhaps this could capture something beyond what message passing can capture. The way we provide the network with curvature information is that we attach to the node features statistics about the local curvature. So we can compute the curvature in the neighborhood of the node. And then we tell the node the minimum and the maximum curvature, and then some kind of summary statistic. It's relatively robust here to what summary statistic we use, but it's important to capture the min and the max. Right, those extremal curvature values are always important to capture, as we've seen with the other applications before. Again, here we have some flexibility on what curvature notion we're using. Ideally, of course, we want to use the most scalable one, since we might have very large, very dense graphs in an application. So this curvature augmentation does, in fact, extend the class of functions that we can learn with the message passing graph neural network. And I want to illustrate this on a specific example. So here you have two graphs, the Rook and the Shikanti graph, which are very famous graphs that are studied a lot in structural graph theory. They have lots of interesting properties. For our purposes here, what's important is that they are regular. They're both 6 regular. And they share a lot of structural properties that make it difficult to distinguish them with graph neural networks architectures. So due to this, that both graphs are 6 regular, we know the one-wise Feiler-Lehmann test or message passing would not do a good job with that. But also beyond that, if we look at common encodings or common structures that are used as encoding, we could, for instance, not use the spectrum of the graph Laplacian here because those two graphs have the same spectrum. We can't look at degree distributions, of course, because there are regular graphs. If we pick the right substructures and count the right substructures, we can maybe distinguish them, but we have to fine-tune that very carefully what substructure we use. So all of those augmentations do not really get us there. However, using curvature, we can reliably distinguish those two graphs. Namely, if you look at that cartoon here, what I've drawn are basically the transport plans that underlie the curvature computation. So suppose we were to compute the curvature of the edge marked in red between U and B. Then the neighborhood of U is colored with blue edges, and then the neighborhood of V is colored with green edges. And then the thin red lines are lines through which in the optimal transport plan a mass, 1 unit of mass would have to be transported. Right? The units of mass are here uniform because we have the same degree everywhere. And you see that on the left graph, we have to transport 1 unit of mass through 3 edges, and then over here through 5 edges. So we get different curvature values in 2 graphs, and even though with other graph characteristics, it would be very hard to distinguish. So in other words, if we use this curvature augmentation, a message passing graph neural network is able to learn different representations for each of those 2 graphs. Now, this is a theoretical example. But this worked also really well in practice. So here are some experimental results for different message passing architectures and different data sets. In each plot, you have in the first row the performance without any encodings, and then you have LA. Here is the Laplacian encoding, and then some other ones that often perform well. But you see here that curvature does a really good job in getting a very significant boost in performance, sometimes more than like 10 points. It's not only in these sort of constructed examples, but this way of capturing structural information over the 2-hop neighborhood and giving that, augmenting the graph so that that's very accessible for the graph neural network seems to also work really well in practice. So those are 2 examples where a curvature, a geometric characterization of the graph using curvature can be really beneficial for graph neural networks. Now, in the remaining time that I have, I want to talk a little bit about this third idea that we discussed earlier of using curvature to understand something about the geometry of the data. And that goes back to continuum limits of Ritchie curvature that I was asked about earlier. The kind of model or the framework that we will use for investigating this are geometric graphs. So for geometric graphs, suppose we have a sample finite sample from some low-dimensional manifold that lies in a space RD. So we have a point cloud. We know nothing about the underlying manifold. We just have some points given in some RD, and maybe we know that they lie on a low-dimensional manifold, but we know absolutely nothing about it. Now, with that point cloud, from the point cloud, we can construct a geometric graph by doing the following. Each point in our point cloud becomes a node in the graph. And then we draw an edge between any two nodes if they're within an epsilon distance of each other. Okay, so we construct these epsilon neighborhoods, and then we get a graph corresponding to epsilon. So as we vary epsilon, basically we get a whole family of graphs that capture something about the metric information in the cloud. Now, what we could ask, and there's a whole body of literature on this question, as we sample more and more points from a manifold, does the sort of geometric information captured by this graph get richer, right? In principle, if we were to look at in the continuum limit at those objects, can we look at this graph and learn something about the geometry of the underlying manifold? And that has been that question has been considered for various different geometric characteristics. In this context here, of course, we are interested in curvature. So in particular, if we look at that geometric graph and we compute discrete curvature on that graph, does that tell us anything about the curvature on the manifold in a local sense? So do we have some sort of pointwise consistency between the curvature on the geometric graph and the curvature on the manifold? And then in the global, we can also ask a global question, namely if the manifold has bounded curvature, bounded Ricci curvature, is that a property that is inherited by the geometric graph? And can we learn that bound from the geometric graph? So before looking at those two questions, I want to point out here that there are sort of two different settings to consider. The first one is where we assume that those epsilon neighborhoods are constructed with respect to the geodesic distance. So with respect to sort of true distances on the manifold. Right, when we measure distances on a manifold, we look at the length of a geodesic, of the shortest path between 2 points on a manifold, and that can be very different than the Euclidean distance between those 2 points in the ambient space. So in the first setting, we assume that we have actual access to those geodesic distances, which of course in practice is not realistic because we don't know the manifold, right? But in the classical literature that looks at these continuum limits, that's a common assumption that's being made. If we want to have something that we could ever hope to use in practice to characterize the geometry of our data, we have to get rid of this assumption and instead approximate geodesic distances from the ambient Euclidean distances that we can actually measure in our data set. Right? So we would be in what we call here setting 2 that uses data-driven approximations of geodesic distances. So what is known about these continuum limits? So first, this first question of approximating geodesic distances from those graphs in the continuum limit that has received a lot of attention, and there's been a lot of work under what conditions that is possible. And there's also quite a bit of work on the graph Laplacian and in what sense of the graph Laplacian of a geometric graph, and in what sense that is consistent with the Laplace Beltrami operator of the underlying manifold. So for instance, work by my co-author here, Nicolas Garcia-Trias, has some really nice work on how the spectrum of the graph Laplacian relates to the spectrum of the Laplace Beltrami operator of the underlying manifold. Ricci curvature has received very little attention in that context. The only work before ours that I'm aware of looks at setting 1. So it assumes access to the true geodesic distances, which in practice we don't have. And it gives asymptotic guarantees. So it says something about the continuum limit, but it can't say anything about the finite sample setting, right? If we want to use that in practice to maybe give an approximation to some geometric characteristic of our data manifold, we need to work in a finite sample regime. We need to say what kind of approximation can we get with endpoints and not only in the continuum limit. So what, in fact, for Ricci curvature and for this notion of Ollivier's curvature that we introduced at the beginning of the talk, we can answer both questions, the local consistency and the global consistency question in setting 2. So with data-driven approximations to the tuneless instances. The kind of results that you get here are stated informally in this box here, right? So we have the Ritchie curvature. This is for the pointwise local consistency result. We have the Ritchie curvature in the neighborhood of the point on the manifold, and then sort of the corresponding curvature that we would compute on the graph. And then we get a quite sort of precise non-asymptotic guarantee that depends on things like the size of the sample, also the dimension of the manifold. You see here that it's somewhat sensitive to how we choose that epsilon, that neighborhood radius. You can imagine if we choose epsilon to be very small, then our geometric graph is going to be essentially disconnected and not capture much geometric information. If we choose a very, very large epsilon, then we have an almost fully connected graph, right? So that will also that will also not capture a good amount of geometric information. So we have to choose this epsilon very carefully. It turns out that one can give sort of some guidance on how to choose the epsilon, but I'm not going to be able to go into in this talk. But there's some something we can do here, some guidance that we can give how to choose that epsilon. And then for the global consistency, the situation is similar again. We can first show that, yes, if the manifold has bounded Ritchie curvature, then that property is inherited by the geometric graph. And we can also learn that bound from the geometric graph. Again, we can do this in setting 2. So using only, assuming only access to Euclidean distances in the ambient space. And we get non-asymptotic bounds that again give us a precise sort of approximation guarantee in terms of the size of the sample, the dimension of the manifold, and so forth. Okay, and just to put this a little bit of context, what we into context, what we can do with those continuum limits. So I think sort of aside from that is a mathematically interesting question to understand. Continuum limits of discrete curvatures and how they actually relate to the sort of standard Ritchie curvature that we have in differential geometry. And there are also a lot of implications that one could consider here for geometric data analysis. So in general, when we talk about characterizing the data geometry or geometric structure of data, a lot of focus has been on characterizing the dimension of the data, right? If we look into classical manifold learning algorithms, for instance, that try to reconstruct a manifold from data, they often have some subroutine or some implicit step where the intrinsic dimension of the manifold is computed. Now, if you actually want to understand the curvature of a manifold, that's much harder, and that's not something that's sort of implicitly done by those manifold learning algorithms. There are a couple of theoretical works like this one that's listed here by Amari and Lefrard that give nice constructions on how to maybe construct data-driven approximations of curvature, but a lot of them are not really practical, very difficult to compute in practice, and oftentimes also only give you sort of one piece of the curvature. Of the curvature tensor and not necessarily Ritchie curvature, such as the reach, for instance. This paper approximates the reach, which is another derivative of sort of the more general notion of curvature. In this work here, we give a way to compute Ritchie curvature from data that is in principle practical. So it's we can construct geometric graphs and we can compute Ollivier's curvature on these geometric graphs that we have constructed. Of course, there are a couple of caveats here. We have to carefully choose the neighborhood radius, for instance. So there are some sort of some technical difficulties that arise in practice, but in principle, it's a technique for computing curvature from data that is implementable and sort of a method that we can use in a data-driven setting. So in a sense, we can think of this technique as maybe being somewhat complementary to what classical manifold learning algorithms, for instance, can do. in that in addition to the intrinsic dimension, we can get some characterization of the intrinsic curvature of a manifold. And then in particular, being able to learn bounds on the curvature or to discover whether a data manifold has bounded Ritchie curvature. That is something that those curvature bounds appear in a lot of classical algorithms. They have connections to sampling, for instance. There are some spectral methods, one of which we discuss in this paper, where having knowledge on a global curvature bound gives us access to convergence rates for certain methods. So there are certainly applications that one can get from if we are able to learn a curvature bound from data. So I'm out of time. I'm going to skip this. So just to summarize, so we discussed notions of discrete curvature that we can compute on graphs via curvature analogies. We also discussed how we can use that curvature characterization of the graph in the context of graph machine learning, in particular related to graph neural networks and overcoming certain challenges in the representational power and the training dynamics of graph neural networks. And then we discussed continuum limits of one of those curvature notions, Ollivier's curvature, and how that is related to characterizing the geometric structure of data. I want to acknowledge here, so in particular, Lukas Fesser is the co-author on the second part of the talk, so using curvature concepts in the context of graph neural networks, and then Nicolas Garcia-Trias is the co-author on the continuum limits of curvature. And here are references if you want to learn more. Thank you.
We're actually good on time for a couple questions. Sure. So yeah, let's have some questions. Could the next speaker please come up too?
You mentioned I wanted to get into. You mentioned you didn't want to get into how we select epsilon for constructing the graph.
Yeah.
Could you at least give us a sense of what how you do that?
Yes. So in order to make this construction work, so you have the standard shortest path distance on graphs, right? That's the metric that we usually endow graphs with. So we measure distances on a graph by looking at the shortest path between two nodes. And then in this setting here, we basically slightly redefine this shortest path distance to account sort of for the length scale that we impose in our data. So there is some construction related to that also has something to do with sort of some of the geometric properties of the manifold that inform how we choose this metric, and that aligns with the length scale. Not sure if that's more clear. It's sort of a longer technical construction. I'm happy to talk about it offline if you're interested. Yeah.
You showed us some bounds, non-asymptotic bounds. How tight are these bounds? Can you discuss them?
Yes. So I believe those bounds are relatively tight. I don't think they could be much improved, but I don't have a proof of tightness.
So the m to the 1 over d looks like trouble, right? If d is large.
I'm not saying that in practice.
Yeah.
In practice, certainly this is
Good is different than tight.
Yes.
But I'm struck. In normal bounds like this, we have m to the s over d, where s is smoothness. You have no hope of exploiting any smoothness in your discrete setting. So isn't that trouble for you?
We can talk more offline. I can yeah. So this is a long conversation. So I don't see how those bounds could be improved. We have some sort of ideas of potential obstacles for improving those, but I don't have a proof of tightness. Yeah.
Yeah, thanks so much. I think my question is similar to Boris's earlier about the when you add edges and remove edges. I'm familiar with like graph sparsening, where you remove some edges and you want a sparse graph that has like similar spectral properties or something. But this seems like the opposite process when you add the edges to kind of bridge these.
So you do both, yeah.
Yeah, you're doing both.
Yeah, so you want to sparsify to kind of combat the over smoothing, but you also want to add a few edges to sort of widen those bottlenecks, right? To combat the over squashing.
So does this have connections to that kind of expander type theory for that?
So they're so not the curvature-based rewiring, but there are other rewiring techniques that people have proposed using those kind of results. Also using like spectral rewiring that uses properties of the spectrum of the graph Laplacian. Yeah.
If there are no more questions, let's thank the speaker again. All you need to do is do your screen share. No? It looks fine. Do you want me to move this out of your way?
Doesn't appear to you.
Okay.
My name is Daniel. This talk is based on joint work with Reza and our advisor Babak, and it's called Universality for the neural dependent kernels with applications. So I'm going to give an overview of the talk first. In my view, the motivation behind most universality results is to understand deep learning better by using some sorts of linearizations for the networks. I'm first going to give a universal result that occurs in the linear setting, and then explain how we linearize problems potentially. And in that setting, we are solving a linear classification problem that is over-parameterized, meaning it has more parameters than training points, which is usually the case in modern machine learning. And we assume that the models are trained via SGD. And then I state a universal result that allows analyzing classification error for non-Gaussian features via analyzing classification error for an equivalent linear problem with Gaussian features. And then I'll explain how to apply to analyze the performance for the neural tangent kernels and for the random features, and I'll also remind what these words mean. And so we can see an illustration for what I just said in the slide. I will sketch a framework that allows reducing analyzing a more complicated problem with non-Gaussian data to a problem with Gaussian data. And then to analyze that, one could potentially invoke one of the tools for dealing with Gaussian features, such as the Gaussian inequalities, the approximate message passing, or just random dynamics theory. And you have probably all heard about a bunch of different universality results, so I'll motivate why we thought we need to introduce one more. First, as far as I'm aware, most universality results stated for regression, and it's to extend those to classification. it's a bit more, there are a bit more technicalities involved, such as the expressions for the generalization error for classifications are much more complicated than just the MSE loss, as it is the case for regression. And then, for example, one also needs to deal with natures of distribution, unlike the regression where everyone just comes from one source. And then there was another previous result for classification, for example, that shows universality of expectation with respect to the gift distribution. And as the authors state in the paper, it is enough to prove universality of the training error, but it seems like it doesn't quite suffice to show universality of the test error, which is the most interesting object for us when we study generalization. And also the setting is a bit different. There's some explicit regularization, so they are not in the interpolating regime. As for limitations for our theorem, the main one is that we were able to prove it only for the SGD. And as I'll explain later, this corresponds to, the SGD corresponds to the minimum of 2 norm interpolator. And while the universality results for regressions, some of them are operate under for much more complicated objectives. Now I'll introduce the setting for the problem. For simplicity, I assume that there are only 2 classes. So model data for each comes from distribution, some distribution PI. And the labels are +1 for the first class and -1 for the second class. Then I assume that we have n denotes the number of data points, and half of them come from one class, half of them come from the other class. And the number of data points is less than the dimension in this case. Yeah, and as I said, it could potentially be extended to the case of multiple classes, but for simplicity, we are just showing the binary case here. Then we train a linear classifier given by some weight vector. And after training the classifier, we just classify according to the sign rule. And then the classification error is defined via the following, where the first term accounts for the probability of taking a point from the first class, but misclassifying it as belonging to the second class, and vice versa, the second term. And then we find W by solving the objective for the following form. And here I need to specify that since the problem is over-parameterized and there is no regularization on W, the solution will interpolate the data. And then also, since the dimension is higher than the number of data points, the interpolation solutions are not unique. So we need to specify which interpolating solution we pick, or another way to say is like what the optimization procedure or the optimizer is. And here we just choose to focus on the stochastic gradient descent. And as an illustration, if we were under-parameterized, then we would have only so many local and global minima. But in the over-parameterized case, for over-parameterized models, we have an entire manifold of interpolating solutions. So yeah, this is why we need to specify how we pick one. For the linear case, this picture is a bit complicated, but for the linear case, this manifold is just some hyperplane. Now I'll say what is so special about the SGD, or how we work with SGD, how we think about SGD technically in this context. So it is known for gradient and stochastic gradient descent that optimizing an objective of the following form, initialized at some W naught, converges to W that interpolates the data and that minimizes the L2 distance to the initialization point.
Can I just ask to see if I understand the setting? So
Right.
you're setting this up like a classification problem, binary classification problem. And then you turn it into almost something that's like a regression on just one oddly.
Yeah.
Got it. Okay. Interesting.
And now, before proceeding to state the theorem, I want to introduce a definition of a matching Gaussian. For classes defined by some distributions pi, we define the Gaussian distribution with the same mean and covariance to be its matching Gaussian distribution, and we'll denote it by n of pi. And then we can construct a Gaussian mixture model corresponding to the binary classification problem by taking n of p1 and n of p2 and combining them. And then it is natural to wonder about the relation between the classifier trained on the original classification problem, that is the mixture of P1 and P2, and the classifier trained of the newly constructed Gaussian mixture model. And then to state the theorem formally, because of the full formal statement would be a bit too technical for a slide. So assume that the data matrix has independent rows sampled from a mixture of two distributions. Then we will need a few other technical assumptions that are listed in the paper, but that are quite general. And Y encodes the vector of labels. And then we take the matching Gaussians, we take the matrix with the rows sampled from the matching Gaussian distribution introduced in the previous slide. And now we solve the objective corresponding to we train the SGD on A and on the matching Gaussian G, which corresponds to solving the following objective according to the implicit regularization property of the SGD. And then denote the corresponding solution by WA and WG respectively. Then we claim that as we take N and D large asymptotically, the classification error does not change. Namely, the misclassification error for the misclassification error of the classifier trained on data sampled from the misclassification error of the classifier obtained from A, tested on data from the mixture of P1 and P2, will in the asymptotics be the same as the classification error of the classifier trained on G and tested on the data from the matching Gaussian for P1 and P2. Here in the slide, I wrote the equality only for the first terms from the definition of the classification error, but it is also true for the second terms of the classification errors parent side asymptotically. And note that for classification here, it's important to both change the distribution we train and we test on, because the expression for the classification error also depends, as a function, also depends on the distribution we test on. Now, after we claim the result for linear classification, I'll introduce the neural tangent kernels to show how we could potentially apply it to neural nets later. So, as we all know, analyzing neural networks in general is very hard. So usually we need to make some simplifications, approximations, and so on. So I will denote the neural network f of x by f of xw, where x is data and w is weight. And then the idea behind this framework is to expand f around w not the initialization point, just by looking at the first term Taylor approximation. And then if this approximation is valid, f becomes linear, approximately linear in w, by the virtue of the fact that we have to introduce, we have to pass x through the gradient of f, and to rephrase, we just get an embedding of x using some feature map. So, and here, even if x was Gaussian initially, after passing through the feature map, it will not anymore be Gaussian. Yeah, and it is also known that if F is fully connected and of large width, then W moves very little during training, and if it is the case, then the approximation is remains valid through training. So again, phi denotes the feature embedding corresponding to the gradient in the linear approximation from the previous slide. And then how you apply universality, we say that, let's say the data was initially sampled from a Gaussian mixture model with some means and some covariances. Then it turns out we can verify assumptions of the universality theorem for the phi of x for this feature embedding. And this gives us an equivalence, summing up the bullets from the previous slide. It gives us an equivalence between the test error of a wide neural net trained on a binary GNN and of a linear classifier trained on another binary GNN whose first and second order statistics come from those of the feature map. And even using this idea, this can still be challenging to analyze, and in the general cases to work in progress. We are working and why this is challenging, because we still have to find the first and second order statistics of phi. That is not that easy in general. And we still need to analyze the corresponding linear problem in detail and draw some meaningful conclusions and insights, not just write down some complicated expressions. So now I'll show an observation that immediately follows from this universality. Denote a network by f of x v and w, where v corresponds to the last layer, and the output of the penultimate layer is called g. So v is the last layer, g is the output of everything before that. And then let's say we initialize the last layer at 0, and note that usually we don't want to introduce to initialize neural networks at 0 because nothing would move. But specifically for the last layer, since that was linear in V, if we initialize it at 0, then after the first step, everything will start moving and training will happen. So it should be fine for training. Then note that by definition, the feature map is comprised of the gradient of f by v and w. And now note that f was linear in v in the last layer, so the gradient of f by w will also be linear in v. But then v was initialized at 0, so the gradient of f by w at the initialization point will just vanish. And we get that phi embeds x into the part that corresponds to the gradient by v only, which is g. So the second part of the embedding doesn't play any role here. And if we contemplate for a second on what it means, it actually means that the performance of this model will be exactly the same asymptotically as if we do not train W at all and just freeze all the previous layers to the initialization point and only train V. Specifically, we initialize V at 0. So I'll now tell what the random features model is. Again, I use the same notation for a neural network and sample all the layers, but the last one at random from a Gaussian distribution. Then freeze W to the initialization and train on the last layer. This model is very easy to train, and it's called random features model, and it's been used in the literature as something that's simpler to analyze, but gives us some insight into how deep neural networks work. And then to sum up the previous slide, we showed that undertaking the last layer to be initialized to 0 in TK yields exactly the same performance as the random features. Unfortunately, however, again, most of them, all analysis I could find in the literature for regression and not activation functions because the setting is easier to work with. But if I missed anything, please let me know so that I wouldn't have to rewrite it. I'll also show a plot corresponding to the previous slide. So we took a network with one hidden layer, took some input dimension bits and a certain number of training samples. Then we sampled the means to be independent, normal, and chose scalar covariances with the coefficient sigma squared over d. And then we chose the quadratic activation function, initialize the last layer at 0 and the previous layer as follows. And then we plotted the classification error in percents for the random feature model and for the fully trained two-layer net, namely where we trained both layers and we observe a very close match between the corresponding performances and the plots of the classification error versus the noise per coordinate sigma. So to give a summary of the talk, we introduced a universality result that can potentially be applied to analyze performance of wide neural networks, assuming the data initially came from a binary mixture model. And we could immediately draw some insight about the relation to the random features model from it. And drawing more general quantitative statements is still a work in progress. And as for the universality result itself, in my opinion, an interesting open question would be generalizing it from just the classifier interpolators trained by SGD, which corresponds to the minimum L2 norm interpolators, to general LP norm interpolators. There is an optimizer that can do that. It's called stochastic LP stochastic nerve descent. Yeah, thank you for attention. Please let me know if you have any questions.
Going back to the main theorem of the talk, so for regression, the error would be just W minus W zeros to the power 2.
Right.
For classification would be this tail of the Gaussian. So my question is, compared to regression where we do CGMT here, what are the challenges you get the test error like the tails? Are there like fundamental challenges to think about? If you want to do CGMT?
Like if you already established universality or
yeah, for universality.
For showing universality or showing so when we are showing universality, we also change the distribution in the definition of the test error. So for the Gaussian, it is the tail of the Gaussian, and for other distribution, the classification error is also potential of a different form. So we need some sort of a CLT type result. That was like the part that we could push strongly for the SGD.
The CLT used. CLT is something you also prove in your paper, the Centralians result?
For the SGD, we were able to show that in a certain sense, the weights come after solving it, like you can think that in a certain technical sense, you can think that your weights come uniformly from a sphere or something like that. And for that, there is a type of SLT in the literature.
Very good.
There was a point in the talk where you said that if you initialize a v is equal to 0, then what happens is that the w's don't change. I was not sure if I understood that correctly, if you could clarify that, but it seemed almost that if they don't change, then it's almost like having the feature extraction fixed and just having the units parental. So could you clarify what I misunderstood there?
Yeah, first of all, in training, they will change a little bit, but as we take N and D to be large, so for our results only says that the performance will be the same as if W was frozen to W naught from the beginning. And I guess in practice it means like that W will move so little compared to V, it doesn't matter. Yeah. Yeah, but I agree that like this means that in this regime it just means that the neural network doesn't perform all that good, because you could as well just train on, if you could as well just train on the last layer, it means that this is not a good regime to work in.
And if you were to argue mathematically, what are the differences between just freezing the feature extraction layer and training the last one versus doing the joint analysis? You're saying that it's very close, but what are the differences?
What do you mean by joint analysis?
If you were to do the analysis, including the dynamics of that.
Yeah, for zero, for initializing the last layer to 0. Yeah, unfortunately, first of all, our results cannot analyze the dynamics. They can be talk only about what happens at convergence, because we appeal to the implicit property of the SGD that characterizes the solution on at convergence. Yeah, for that, if we initialize at 0, we just know that asymptotically, if like you move both, the performance will still be as if you trained only last layer. So the conclusion is that again, the feature extraction layer will move so little, it will not matter compared to how much V moves.
Thank you. I have another question. So you only focus on the overparameterized case.
Right.
So the reason for that is because you want the implicit formula, formula. So if you lift that, so what will the challenge be? So if you want to lift the overparameterized assumption, what should we do in that case?
Like if you're underparameterized?
We are underparameterized.
Yeah, I mean,
does it hold, or it's like a proof issue? Does universality hold there?
Yeah, I think so. Just was less interesting because usually we are overparameterized.
I have a follow-up question. So when you say that the intermediate features or intermediate race don't train, so you are in some sort of NTA regime where the activations don't get much update in the intermediate layers.
Right.
And is that true? And only the last layer is trained. Is that true?
Yeah, this is the conclusion.
Okay, so this is also true in your experiments. So
Oh,
you said in your experiments
yeah,
the random feature model and the performance of a deep network.
Yeah, I see what you're saying. It's, yeah, I didn't look at it. I looked only at the performance in the experiments.
Okay.
But yeah, it's a good suggestion to look at. Thank you.
Okay, let's maybe thank the speaker one more time. Just wanted to announce, so thank you so much. So yeah, the posters will be downstairs. So if you want some coffee or snack, grab that now, go downstairs. Lunch will be back up here though. So the food will be swapped out at some point too. And Renee, did you have something to add?
Yeah, so lunch will be served here behind me, and then you can eat right here. So once the poster session is 12:30, just come out.
Yeah.
Yeah, I think there's a. That's true.
Okay, perfect. All right, good afternoon, welcome back. My name is Jeremiah. I'm assistant professor at Johns Hopkins. I'm part of the organizing committee. So welcome to the last stretch of DeepMath in this afternoon. It's my great pleasure to introduce Boris. Boris is an assistant professor at Princeton at Orphe and operations research. He has done a lot of really cool work on trying to come up with mathematical tools to understand what's happening with deep networks. He's also won several awards, including the Sloan Fellowship, the NSF Career Award, among others. And he's here to tell us about scaling laws in networks. So Boris, thanks for joining us.
Okay. So thank you so much for the introduction. Let me just say, I've had a lot of fun talking to people at the posters, listening to talks this morning, so this has been great. Okay, so I'm really excited to share with you all kind of my favorite sets of questions to ask about neural networks or machine learning models. In general, I call it neural network scaling limits. Okay, so I'll explain exactly what it means, but kind of in a nutshell, I'm basically interested in understanding something about how to characterize learning with neural networks, ideally in the regime where both the model is large and the number of data points is large too. Okay, so that's kind of what I think of as the practical regime, and that leads to a bunch of mathematical questions, which I'll walk through. But I don't want to assume that everyone here knows exactly what I mean by this kind of analysis of neural networks. Okay, so hopefully you'll bear with me for just a little bit. I'm going to walk us through at least my notation for things. And okay, so feel free to stop and ask me questions in the middle. I prepared on purpose more slides than I can hope to cover, and so therefore I don't feel any urgency to get through all of them. Yeah, I think that's a good psychological tactic. Okay, let's see if I can't progress. Oh, here we go. Okay, so first of all, what do I mean by neural network? Okay, we all know neural networks are parameterized, high-dimensional families of functions. So for me, in most of the talk, I'll consider just fully connected neural networks. And this is just my excuse to tell me the notation. Okay, so the inputs to the models I call little x. These are n zero-dimensional vectors. So n0 is my input dimension. Then the output is, I write zl plus 1 of x and theta. So capital L is the depth, it's the number of layers in the model. Theta is my parameters. And as usual in fully connected networks, we start with x. Then we apply a simple hidden layer where we multiply x by a matrix of weights. So my notation is that this first weight matrix is n1 by n0. And then to each entry of that n1 dimensional vector, you apply the same nonlinear function, sigma. At least for most of the talk, the nonlinearity is going to be sigma. We do this capital L times, and then finally the output of the network is just a linear readout from this final hidden layer. Okay, so that's what I mean mainly by neural network in this talk. And as you'll see, I prefer pictures. I'm not very good with formulas. And so I tend to think about neural networks in two ways. So on the left is what I imagine a computer thinks of a neural network as looking. Okay, so to a computer, I feel like a neural network is just this big list of parameters. So you have theta, and it lives in this big featureless space where the dimension is the number of parameters. And it could be very large. I think of it as being millions, billions, okay, sometimes trillions, depending on how ambitious you are. Okay, so, but in some sense, although this is an oversimplification, most of my talk is really trying to understand this rather complicated map, which maps the current setting of parameters that you have, theta, to the actual function you get when you set your parameters to be that. Right? And the reason this is a difficult thing to understand is the map from the parameters to the actual functions is very nonlinear. Okay, so don't take the picture too seriously, but I just think of, you move theta over here and z moves around, sometimes in unpredictable ways. And so I've drawn a cartoon of some manifold over here. Okay, so this is how I imagine a computer imagines that I think about a neural network, roughly speaking. Okay, very good. Okay, so the kinds of questions I'm mainly interested in come from the way we actually use neural networks in practice. So I think for this crowd, you all know this, but nonetheless, this will, again, let me tell you the notation that I like. See if I can't progress this forward. There we go. Okay, so for me, the typical use is you start with a data set. I'll typically write my data set as script D, and I write little n for the number of samples. Okay, so I observe this unknown, the values of this unknown function f at some inputs xi, maybe exact values, maybe inexact values. It doesn't matter, obviously, for this cartoon. Okay, and I'm an optimist at heart. If you don't know me, that's a true statement. So I believe this function f, or maybe some very good approximation to it, really lies in the space of functions I can compute with a neural network. Again, my job in life, or at least this is what I tell my funding agencies, is to find this f. Okay, I have other jobs in life. I have a daughter and things like that. Okay, they don't know about that aspect of my life. Okay, so how do we do it? Well, we have to do some kind of optimization, right? And at least for me, so the optimization has two steps. So step number one is an initialization phase, where you basically say, look, I have no idea where my initial setting of parameters is going to be that is actually going to be good for fitting the function f. So I choose my parameters at random. And the way I've tried to draw the picture is the probability distribution you put on the parameters is very simple-minded from the point of view of the parameter space. Just think of every weight as being an independent Gaussian. Okay, that's the cartoon on the left. But because the map from the left to the right is complicated, I think of sampling the initial function I start with, this function z of kind of dot colon theta naught, as being fairly complicated. And an interesting and important chapter, I think, in deep learning theory is to explain, well, what kinds of functions are we starting with when we do optimization? Because as we know, there are many ways to fit the training data. So where you actually start influences where you end. Okay, but initialization is not all there is. What we then do is we just iteratively improve our guess for the parameter vector theta by some version of a first order method. Okay, so we just take a small step in the direction of the negative gradient of some empirical risk over the training data, which I generically call L for a loss function. Okay, so it's hard to prove theorems and easy to draw pictures. That's why I like pictures, right? And so we take some set of steps here on the left, who knows? And I told you I'm an optimist. So I hope the set of steps eventually leads me to F. Okay, so that's what I mean by using a neural network, and that's just kind of my notation for what's going on. Let me just stop for 1 second in case something is not clear. Because if this isn't clear, it's going to be a disaster. Okay, it might already be a disaster, but it's like a necessary condition that the notation is clear. It's okay. I feel like it's got to be pretty clear for people in this room, maybe. Okay, fine. So I promised to make the talk self-contained. So I told you what a neural network is. Now I have to tell you a little bit what I mean by the other words in the title, namely what's a scaling limit. Okay, so in some sense, scaling limits are, that's the word that I used when I was growing up doing mathematical physics for trying to understand the properties of systems where the system is very large. Okay, so I'm just recapitulating what my neural network looks like. It's up here. And okay, in one word, when I say scaling limit, I say, look, neural networks have a lot of parameters which are potentially large and often large in practice. Okay, the number of neurons in each layer, which I just generically denote by n, that's the width. The number of layers in the model, L, is the depth. The number of samples, there are many other things. Your compute budget could be large, your input dimension can be large. There's lots of kind of large parameters in the problem. And okay, at least if you're like me, for some reason, I can't explain why, I've always loved asymptotic problems. So I want to take everything to infinity, okay, and try to figure out what's going on. So when I say scaling limit, I mean the analysis of neural networks when at least one and maybe all of these large parameters are large. Okay, so I'll walk you through the neural network side of things, but just to get you kind of thinking along the same lines that I think, I want to walk through two rather classical examples of scaling limits, which are very, very special cases of neural network scaling limits, just to kind of remind you and kind of emphasize that these scaling limits are subtle and there's something kind of interesting, both practically and mathematically. Okay, so the first scaling limit is, I'm going to take us back to like 1950 or something like that. Okay, not as if I was alive in 1950, but I'm going to have 0 hidden layers, L equals 0. So my model is just z of x and theta is W1 times x. Okay, just a linear model. And I'm going to, on purpose, look at the most generic thing I can hope to learn. So I have some inputs xi, which are just isotropic Gaussians in an n-dimensional space, IID. And I'm trying to learn the secret direction beta. And what I observe is beta transpose xi plus noise. Okay, there's no more classical kind of problem in learning in high dimensions than this. Okay, so I told you I like pictures. So here's my picture. So I think to myself, look, there are two large parameters in this problem. The number of samples I observe, the number of features, or the dimension in which everything lives. So let's imagine we're somewhere in this space of models. So maybe imagine we observe 1 million samples in a 3 million dimensional space. That's not totally crazy for modern kind of applications. Okay, so my dream as a theory person, at least, is to say, look, both little n and big N are pretty big. At least that's how I view them. So in some sense, I should be close to this corner infinity comma infinity. Okay, and so in what sense am I going to be close? Well, okay, I can try various senses. So sense number one that I can try, I don't know why this clicker doesn't work super well. There we go. Is I could say, look, maybe I'm close to this point infinity in the following kind of precise mathematical sense. I'm going to fix the number of samples, and I'm going to let the number of features go to infinity first. Then I'm going to take the limit as the number of samples goes to infinity. That's a like mathematically well-defined sequence of limits that I could study. And I could ask about, various forms of learning for beta. Just think of learning beta by least squares regression or something like that. So this is very sad and is a disaster. Okay, so you don't want to do this. Why? Because in this regime, you're in an infinite dimensional space and you observe little n completely orthogonal vectors. And your vector beta has zero overlap with probability 1 with any one of them. And therefore, the best thing you can do is always predict 0 on new examples you haven't seen. Okay, that's the only game there is in town. So you just got fired from like your 1950s machine learning job. Okay, very bad. Okay, so that's not a good set of limits to take. That's not a good sense in which this practical thing is close to an object that you'd like to analyze mathematically. Okay, so you can hope to go the other way. You can say, well, let me try the opposite. I'm going to fix the dimension of the space. I'm going to take the number of samples to infinity first. And then I'm going to go up and take the number of features to infinity. Okay, so that's a little more sensible, but not too much more sensible. Okay, that's like a regime in which you've observed like e to the n projections of beta. Okay, so you pretty much have observed every projection of beta that exists. And all you can do is hope to regularize the noise away a little bit. Okay, so that's a problem you can solve. You can ask what's the best regularization, but you're going to get terrible answers if you try to use that amount of regularization at this model that you actually started with. Okay, so the question is, what am I supposed to do? Okay, and the answer is classic. So the answer goes like this. When you do linear regression in high dimensions, what you know is that the key object is the sample covariance matrix of the x's. Okay, the sum of xi transpose. And everything has to do with the spectrum of this matrix. So think about the Marchenko-Pastur law. Okay, so what kind of classical high-dimensional statistics or random matrix theory tells us is that this model you're actually starting with here is only close to other large models if you keep the ratio of little n to big N constant. It's like the effective number of samples that you observe. Okay, so if you want an infinite size model to analyze so that answers at infinity are actually going to be close to answers for the model that you started with, you need to take both little n and big N to infinity together at a fixed ratio. That's the game you have to play. Yeah, please.
You can say once again, what was the issue with the second limit where the number of features was first?
I mean, so it's basically like you have an exponential number of projections of your hidden vector beta with a little bit of noise on top. So you basically have observed every projection of beta you can hope, and all you have to do is regularize the noise a little bit, and you can do a little epsilon better, epsilon worse than generalization. But you see here, it's like there are 3 million directions, but you've only observed the projection of beta onto a third of them. So you have much less information about beta. You got to regularize way more. That's the kind of thing that happens. Okay, so the mathematical point I'm trying to make is that most scaling limits, most interesting scaling limits have the property that the various limits as the parameters go to infinity don't commute. Okay, that's the kind of picture I'm trying to draw. Okay, so this is my 1950s example. So now let me go to the 1960s. Okay, so this is going to be the following situation. So I'm going to take the nonlinearity in my model to just be the identity. Okay, so I just have a product of matrices times x. And in fact, I'm not going to do any training whatsoever. I'm going to ask what happens at initialization. So then what you're studying is you're studying a product of, roughly speaking, L IID random matrices with appropriately scaled Gaussian entries. Okay, so products of random matrices have been studied truly forever in the random matrix theory and probability literature. Some of the earliest papers go back to Furstenberg, for example, in the 60s, but it doesn't matter. Very broadly, studying the limit as the depth, the number of terms in the matrix product, and the width, the size of the matrices go to infinity, has been done in like plus infinity papers. Okay, what I mean is you can never read all the papers that have been written. So it's like effectively plus infinity. And mainly the analysis has been done in two regimes. Okay, you fix the number of terms in the matrix product. That's like fixing the polynomial you're going to study. And then you evaluate that polynomial in matrices, random matrices of growing size. Okay, that's like the free probability regime. This is like Wigner's semicircle law or the Marchenko-Pasteur distribution or whatever you want. That's kind of what lives up here. It's like this beautiful theory. Okay, but there's an equally well-studied world where you study what's called the multiplicative ergodic theorem, or kind of the world of Lyapunov exponents. The way you think about it is you think of this as being like a dynamical system where that's very chaotic, and time-one evolution is you multiply it by a new random matrix. Again, you ask what happens at long times. So that's why it's kind of an ergodic theory question. And so there are a million papers that ask what happens to products of random matrices. This comes up everywhere. It comes up, believe it or not, in like theories of quantum gravity. And it comes up in the analysis of SGD and okay, whatever. It comes up all over the place. And the basic point, and I'll explain this a bit more carefully later, is that these two limits are highly non-commutative. Okay, so and what we'll see is that the right sort of parameter for interpolating between these two regimes is you're supposed to, it turns out, take the ratio of the number of matrices by the size of the matrix to be a constant, and then take the limit. And that's going to give a reasonable way of interpolating between the two regimes in such a way that if both L and N were actually big, going to infinity is a pretty good approximation to your finite but large model. Okay, so really these are just very special cases of neural network scaling limits. And the kinds of questions I'm interested in is, well, what if the number of samples and the depth and the width are large? What if the nonlinearity is not the identity? I probably won't have time to talk about it, but I'm interested in doing this for residual networks and for transformers and for other architectures, not just fully connected, but the fully connected story is already quite interesting. So that's my introduction to what I mean by scaling. So let me just stop for 1 second, because my plan is I basically want to walk you through several scaling limits in increasing order of complexity, or at least chronologically. And I'll tell you a little bit about what's known and a little bit about what I did and kind of why I think it's exciting and what I like and don't like and so on. Yeah.
Yeah, what do you mean by what happens? Like, because there are many aspects one can study the neural networks and learning. So what aspects are you addressing?
So I'm both an optimist and I'm kind of hopelessly optimistic. So my goal ideally is to just describe to you everything about learning. You give me the statistics of the training data, I take the limit as the number of data points, model size, whatever goes to infinity, and I just write down for you a set of equations about here's what you learn. Now, sometimes you can do it and sometimes you can't, but like, I don't think it's completely unreasonable to ask for that. Yeah.
Thank you.
So, I mean, it's a fair question. You'll see what I can prove, and maybe that's a better answer. Yeah.
Sorry, just to understand your hopeless optimism.
Yes.
Are we going to restrict ourselves to IID parameters?
No.
Okay.
Well, I mean, there'll be IID at initialization, and then there's going to be some learning.
Okay.
And some theorems will be about initialization, and some theorems will be about learning, and you prove what you can. Yeah.
So what's the motivation of sending the depth of the network between? So if you think of modern architecture, the width is always huge, but the depth is always like something, at least the models that I know of, is almost like bounding, it's small. Right?
So I guess what I would say is, in practice, everything is finite. And so like, for me, I was kind of trained as a statistical physicist, at least in some sense. So, I go to infinity, but then I do perturbation theory to understand the effects of finite depth and finite width. So suppose I told you that the right thing to study is something is controlled by e to the depth divided by the width. Maybe then all of a sudden, if the depth is 5 and the width is 1,000, that's actually like a reasonable number. So it's one of these things, you don't know what you're going to get till you get something interesting. That's kind of my feeling. But it's a totally fair question. I mean, I would say width 1,000 is reasonable in practice. Depth 5 or 10 is fine. So maybe it's 0.01. That's also like another way of saying it's like a non-zero number. So who knows if that's close to zero. Okay, very good. So let me start. I'm going to start in almost prehistoric neural network days with the simplest of all possible scaling limits for neural networks, which is alternatively called the kernel regime or the lazy regime or the linear regime. Anytime something has a lot of names means it's well studied, I feel. Okay, so I'm just reminding you this is the kind of network that we have, and this is how we initialize the model. Okay, so I'm just going to put together like many papers. I'm not going to attempt to do a review, but the basic point is that there are many results going at least back to Radford Neal in the early mid-90s, and then kind of more recent results, which basically say the following thing. They say, let's fix the input dimension, so the dimension of the x's, and the output dimension, the dimension of the z's. Let's fix the number of training data points we're going to have, and let's send all the hidden layer widths to infinity.
Okay, so the depth is fixed and all the hidden layer widths go to infinity. Then you find the following thing. So first of all, at initialization, the neural networks are extremely simple. I drew this complicated thing in the beginning of the presentation, and I tried to suggest to you that the distribution you get over outputs is complicated. But in this limit, it's not. You just get a Gaussian process. Couldn't be any simpler as far as a starting point. But this is just kind of the tip of the iceberg. Neural networks are very simple for the purposes of optimization as well. Okay, so roughly speaking, what happens is if you have a regression task, so think of mean squared error regression is kind of the task we're doing over a fixed data set, then actually neural networks just become linear models. They become a kernel method where you apply the following feature map. So to each x, you simply replace it by the gradient of the model with respect to its parameters at initialization at that x. Okay, so depending on your mindset, you might say, this is great news. Secretly, neural networks in this regime are linear models. I know a lot about linear models, so I'm happy. But you could also say, this is like terrible news. The whole point of neural networks is that they're supposed to be nonlinear models. They're supposed to learn data adaptive features. That's how pre-training and then fine-tuning is supposed to work. So, okay, so this is like the analog of one of these scaling limits, which is not a sensible one in retrospect. It's like the starting point for a lot of analysis, though. Okay, so maybe a good point about this scaling limit is it does suggest why optimization might be successful in practice. If I tell you basically your network is a linear model and you have a quadratic function of the outputs of the network as your loss, you're basically just doing convex optimization. So that's good. You can fit the data. But of course, there's no feature learning. Okay, except, and this is kind of from my point of view, the interesting and good news from this limit, that this result that I've stated, or this set of results, is unbelievably brittle. If you change any assumption, you're basically going to violate the conclusion. Okay, so for example, if you just study things at finite width, you're not going to get a linear model. You're going to get interesting finite width corrections. And I'll say something about that. If you study things at large depth, these turn out to be the same thing, essentially. You'll get interesting corrections to this kernel regime. If you send the number of data points to infinity together with the width of the model, you won't be in the kernel regime. If you do what's called the mean field initialization, you kind of reparameterize the network a little bit. You change in seemingly small ways the optimizer. You're not going to be doing linear regression at all. You'll be doing Wasserstein gradient flow, okay, at least for one-layer networks, and more complicated analogs for more general networks. Okay, so for me, this is like a starting point, and I'm going to tell you about these other scaling limits, but I have to kind of start here. Okay, and I should have had like 50 names here to like tell you what people did. I did things that mathematicians might love. I did things like prove universality for these Gaussian process limits with respect to the distribution of the weights and the nonlinearity and all that. So that's why I've subtly included myself here. Yeah.
Just for clarification, you said that the map is linear, but the feature map is non-linear. What you have is a linear model on that feature.
Correct. So when I say linear model, I only mean linear in parameters. That's like, that's, yeah. You have a data independent feature map.
Yep.
And like you just learn linear model.
Yep.
Yeah. So, but you're right. It's not linear analysis for sure. Yeah.
Okay, no question. What constitutes feature here? Very much linear model, but in a sense, you learning which features are.
So okay, so you're right. So there are several possible definitions, but for me, I say there's no feature learning if there exists a linear model. So that learning with that linear model is equivalent to learning with your neural network.
So that's the linearity.
Yes, correct. That's my definition of feature learning. Usually the components of this feature map are called the features, and you learn a linear combination of them. At least that's the terminology I use. Okay, excellent. So this limit I don't like because you get a linear model, but you know, the thing I was always taught when you have a limit, like you send the width to infinity, you should compute the 1/n correction to this limit and then see how it couples to the other large parameters in your problem. In this case, I'll tell you about the depth. Okay, so that's what I'm about to do. But before I do that, okay, so I was told back when I was a graduate student, 70,000 years ago, seemingly, by my advisor that okay, a good talk has to have 4 ingredients. So you have to have a picture, a proof, a theorem, and a joke. Okay, and the key point is that the joke and the theorem have to be different. Okay. So okay, that was my joke. So I gave you a theorem, I have to give you a picture and a proof now. So this is my favorite proof. This is the simplest calculation I know how to do with neural networks. And I just want to give you a little bit of an intuition for why the limit as depth and width go to infinity don't commute, and why the right thing is the ratio of the depth to the width, at least for these fully connected networks. Okay, so I'm going to study the simplest thing I can imagine to explain this. So I'm just going to study this deep linear network. So I took out the nonlinearity. And I'm going to study the model at initialization. Okay, so I have n by n weight matrices. I have capital L of them, and each entry is initialized to be Gaussian mean zero variance 1 over n, and I fix an input x that has norm 1. Okay, so my goal is going to be to do this. I'm going to study the absolute simplest random variable you can imagine that comes from this model. I fix my x, I get a random vector as the output, and I just study what's the norm of this random vector. Okay, it can't be anything simpler. Okay, so maybe for the graduate students in the room, or maybe if you're just a graduate student at heart, okay, here's question number 1, just to see if anyone wants to take a stab. So suppose I fix the depth of the model, anything you want, L is 5, and I take the width to infinity. What does this random variable converge to? Melanie doesn't get to answer because she's heard this stuff. Also, she probably knew the answer before she heard the talk. What am I going to get? There's only 3 possible answers, right? 0, 1, infinity. Isn't that how it is? Okay, so the fact from random matrix theory to remember is when you have an n by n matrix and you scale the entries IID in this way, that it preserves with high probability, with a high degree of accuracy, any finite number of lengths and angles. These things are like isometries. Okay, so if you have a finite number of these matrices, they're going to preserve in particular the length of x, so they'll be very close. So you take the width to infinity, and you just recover the length of x, which is 1. Okay, you can get 1 almost surely in this limit. Okay, very good. So now, you can imagine which limit I want to take next. I can get the clicker to work. There we go. Okay, so now let's fix the size of the matrices. Okay, they're 2 by 2 matrices, let's say. And take the depth to infinity. And I ask, what happens to this random matrix product when I apply it to my random vector, or to my fixed vector, doesn't matter. Well, okay, so here what you have to know, and this is maybe slightly less well known, but it's a kind of classic fact. Take a product of L things, and you raise them to the 1 over L power. That kind of is a reasonable normalization. Then the singular values become between 0 and 1. They converge to a distribution supported on 0, 1. Okay, so if you don't raise it to the 1 over L power, it's like you're taking something supported on 0, 1 and raising it to a higher and higher power. All the singular values go to 0. Okay, that's what happens. Bam, you get 0. Okay, so look, already this is a random variable where clearly the limits as n and L go to infinity don't commute. Okay, but this is such a simple random variable actually that we can figure out exactly what the distribution is. Okay, so let's do it. This is the calculation part. And I think it's an instructive calculation, even though it's rather simple. Okay, so step 1, you use the definition. That's what I tell my undergrads. Don't use the definition, you're going to fail in solving the problem. Okay, so the main idea is to basically isolate the action of each weight matrix separately. So how do you do it? Well, you just, for example, multiply by and divide by the norm of W1 times X. And then you just stare at it for a moment, and you are instantly going to be happy once you see it. Okay, so W1 times X is a Gaussian random vector, right? W is a Gaussian random matrix. It doesn't matter which X I chose. Could have been the first basis vector. So just think of that as the first column of W. So this is a Gaussian random vector. So its norm has a well-known distribution. It's basically a chi-squared distribution. Okay, but just as importantly, the norm is independent of the direction, right? Gaussian random vector is uniformly random on the sphere. So actually, these two things are independent. And okay, W2 is also a Gaussian matrix, so it doesn't matter which unit vector I took here. Okay, so I get to write in distribution that my random variable is actually a product of this appropriately scaled chi-squared distribution times the same thing where I have 1 less matrix in my product. Okay, so obviously I've made some progress. I feel very good. At least that's how I think about it. So what do? You do this L times, and you learn something which I think is kind of neat. You get this exact equality in distribution that the norm of this output of the network is a product of L IID random variables. Okay, and you can already see the fight between N and L happening. So each of these chi-squared random variables wants to concentrate around its mean as you grow N, and its mean is 1. That's the way I normalized it. So that's why we get 1 up here. But the L accentuates the fluctuations, right? They're all 1 plus or minus a little error. And so the bigger L goes, the further you deviate away from this regime. Okay, so just to be a normal human being, I write this in some more sensible way. So I put everything in the exponent, and I see that my random variable is e to a sum of IID random variables, just these log chi-squared things. Okay, just trust me when I say I know the mean and variance of these log chi-squared random variables, and each of them is on the order of 1 over n. Okay, so if you think of L being large, you can just apply the central limit theorem here. And what you learn is that your random variable looks like e to a Gaussian, where the mean and the variance both scale like L over n. Okay, and the reason they scale like L over n is that each of the matrices gave you a 1 over n correction in the exponent, and they're L over. So that's why L over n appears. And so what you find is that you should really be taking n and L to infinity together at a fixed ratio if you want to have an interesting limit. And this limit interpolates from one regime to another. Okay, up here L over n was 0. And so that's like a Gaussian with mean 0, variance 0. E to the 0 is 1. I got it right. At least I didn't obviously mess up. Right, and down here L over n is infinity. So you get e to a Gaussian with mean minus infinity, standard deviation square root of infinity. So you get e to the minus infinity, which is 0. Okay, and you see that it nicely interpolates between these two limits. Okay, so of course, this is just a very special calculation. And I've actually spent a bunch of time working out the random matrix theory more generally for these matrix products. Not just these linear statistics, but the spectrum. It's actually a lot of beautiful, still open problems. But it doesn't matter. This is like the tip of the iceberg for what's about to happen for neural networks when you put in a nonlinearity as well. Every layer of your network is going to be close to your Gaussian process limit, at least at initialization, but there's going to be a 1 over n correction. And then you're going to get an L over n as the correction, basically, for the neural network as well. Okay, let me just stop for 1 second before I present the theorem. See if this is okay, or people have questions or comments. Okay, my eyes is happy. That makes me happy. Well, I guess I'm pretty happy anyway, but it doesn't make me any less happy, you know? So, okay. All right, very good. So let's go. So version 2 of scaling limits. Okay, so now I'm going to say, well, suppose I have one of these fully connected networks again, and I initialize just like I did in the NTK regime. So I'm not doing the mean field parameterization. I'm quite interested in that, but I'm not going to present really anything about it today. Okay, but I'm going to take both the width and the depth to be large. That's the game I'm going to play. Okay, so I played that game for a long time. Okay, many nights were spent, you know, doing calculations of various kinds. So I took like a bunch of papers that I wrote and a bunch of papers that other people wrote, and I smushed them into like 25 characters because I'm from like the Twitter generation or something like that. Okay, here's the basic point. I'll state some precise results in just a moment. So if you take all the widths of the network to be proportional to a large constant n, so large but not infinite, then this ratio L over n plays the role of what we call the effective depth of the neural network. Okay, I'll explain in what sense I mean the effective depth. So for example, so I told you before, if you fix the depth of the neural network and you take the width to infinity, you're supposed to get a Gaussian process. Okay, so one of the things I was interested in is how close am I to this Gaussian process when n is large but finite? And so one way you can calculate this is you can study the cumulants of your stochastic process. Okay, so the odd cumulants vanish because you have a weight matrix out in front, so just by symmetry, all the odd ones are gone. So only the even cumulants are interesting. And what I proved is the following sharp estimate. Okay, so if you fix the depth, you let the width go to infinity, all the cumulants of the output of your random network, this is only at initialization in this theorem, go to 0 like this. Okay, so the second cumulant, when k equals 1, doesn't go to 0 at all. And that's because the second cumulant is the covariance function of your process. You're supposed to get a Gaussian process. So that's fair. But then the fourth cumulant goes to 0 like 1 over n. And the sixth cumulant goes to 0 like 1 over n squared, and so on. Okay, so this sometimes has a name. This is called like hierarchical clustering. Okay, at least by some. Doesn't matter. This was like a result you can prove. But okay, I tried to be honest. I try to be honest in all my talks, though I fail a little bit, of course, because you have to compress lots of stuff. So clearly the constant depends on the nonlinearity, on the depth, but also on the nonlinearity and other things which I'm suppressing. So if you just ask, how does it depend on the depth? Well, what you find is actually something pretty cool. I think it's cool. Okay, so no matter which cumulant you look at, no matter how small it is as a function of n, it actually grows like L to the appropriate power. Okay, so if the depth and the width are both large, you're actually not close to a Gaussian process at initialization at all. There's some other distribution that you're close to, which has all non-zero cumulants. Okay, that's like, so think of this as this is what happens after 0 steps of training. And you can kind of see why L over N plays the role of an effective depth, right? If you had a depth 0 model, if you just had W1 times X, then you're supposed to get a Gaussian process. That's exactly what happens with depth 0 models. And I'm telling you, you get a Gaussian process if and only if L over N goes to 0. So L over N is like a better measure of how deep you actually are. Okay, so that's 0 steps of optimization. But okay, what comes after 0 is 1, right? So let's do 1 step of optimization. So one of the problems people struggled with for a long time with neural networks is called the exploding and vanishing gradient problem. A lot of things people invented were actually to mitigate this issue. And roughly speaking, this is like a numerical stability problem with training networks where your gradients have very high variance. Okay, sometimes they're very big, sometimes they're very small. If they're too small, nothing happens. If they're too big, you diverge. Neither situation is good. So if you want, this is the study of 1 step of training, and you can ask, well, how does the variance of these neural network gradients actually scale? So again, it turns out if you fix the depth and you let the width go to infinity, you get the gradients of some reasonable Gaussian process. They're order 1. So the variance goes to 0 in the appropriate sense. You just get order 1 gradients. But actually, the way the variance scales, it scales like L over N. So if L over N is too big, you're going to be more and more and more unstable. And this is a reason, I forget who was asking me, that at least in retrospect, if you train these fully connected networks, you shouldn't go too deep. If it's too deep, you're actually going to have a big problem. Okay, so this suggests don't keep L over N to be too big. Okay, and the next thing, which is kind of the analysis of 2 steps of training, if you want to think of it that way, is how close to a linear model are you? So I study the Hessian of the model around initialization, right? So you're a linear model if your Hessian is 0, and that's a reasonable definition of linear model. And so indeed, if you fix the depth and you measure the norm of the Hessian in the appropriate norm, then it goes to 0 like 1 over N. But actually, as you have more and more layers in the model, the norm of the Hessian grows like L over N. Okay, so this is, again, a precise sense in which L over N is the effective depth. If L over N goes to 0, you get a depth 0 neural network, also known as a linear model. Okay, so there are further results here. These results are all kind of mathematically exactly precise. I had some results that are more physicsy in nature, which are certainly right, but less kind of accurate in their proofs in certain places. And we proved, at least at fixed data set size, if you have just mean squared error regression, that L over N also controls after training the distance between what you would have gotten with the NTK regime and what you actually get with your neural network. Okay, so I just haven't included. Okay, so let me just stop again for 1 second here. I know I've kind of put a lot of stuff into one slide, but I find it's better to give like a broader overview than go through every detail of each result. Yeah, please.
Can you say something at least intuitively on which is the stochastic process that describe your network and L over N?
Yeah, so that's a complicated question. The short answer is what we did is we computed the L over N and the L over N quantity squared correction. So we basically computed the 4-point function and the 6-point function. And we can compute all the connected correlators in principle, but we don't know how to do it in closed form. So it's painful and it's something. And I'd like to know what it is better as well.
But do you think it's possible?
Well, I'm an optimist, remember, so definitely. No, I'm sure it's possible. Look, people have done much harder calculations. It's just like, I'm not that good at doing stuff. That's fine. Thank you. Other questions? Yeah.
You said this is the NHK rescaling, right? And the mean field rescaling and then you get like a different set of.
Okay, great question. So actually, fun fact. If you do the mean field parameterization calculation, but you let the depth be big, you find that NTK and mean field are the same thing. So if you fix the depth, like, you have this extra 1 over square root of n multiplier on the output of the network, but actually that multiplier is a 1 over square root of n divided by L. So as soon as n over L is positive, actually NTK and mean field are the same. It's 2 seemingly different, but ultimately the same way of leaving the kernel. So you can think of this as being the mean field scale too. Okay, very good. So that's scaling version 2. So okay, I told you I like pictures better. So roughly, okay, some of this is proved, some of this is conjectural. I think of this as the phase diagram of these deep and wide MLPs at a fixed number of data points. So you have this L over N, which plays the role of the effective depth. And if L over N is too small, you don't learn any features because you're too close to a linear model. And if L over N is too big, you don't learn anything because you're not numerically stable. So L over N should be kind of like reasonable. That's my kind of TLDR. Okay. So now let me go to scaling limit version 3. Okay, so the thing I really don't like about what I just presented to you is I had to fix the number of training data points. Oh, that's so painful. So painful. Because in the real world, like the basic fact of the matter is the more data you have, the larger model you tend to train. That's how it works, typically at least. And so I wanted to find a regime where you could understand the dynamics of learning or what happens after training, when the depth and the width and the number of samples could all go to infinity together. Okay, so I was desperate. So I took the following model, and I'll explain it. So I'm not going to do learning by SGD. I'm working on the learning by SGD now. So ask me in 6 months. I think it's doable, but it's harder than this, at least for me. So take the following model, deep linear network. Okay, you just know nonlinearity. The output is linear x. And in fact, I take the output dimension to be 1. So you can just think of this product of matrices as a really bizarre way of parameterizing a single vector theta. Okay, that's all it is. Okay, so then I observe little n data points, and I put myself in a situation where I'm over-parameterized, and I can exactly fit all my training data. So what that comes down to is the number of observations needs to be strictly smaller than the dimension of the vectors theta and x. Okay, so here's my cartoon. There's a whole hyperplane of thetas that exactly fit the training data. It's just a set of solutions to this underdetermined set of linear equations. Okay, theta transpose xi equals yi. And theta star is my minimal norm interpolant of the data. Okay, so the basic linear algebra, right, is that orthogonal to this space of the solutions is the span of the xi's. These are the directions in which, if you change theta, you change the prediction on the training data. And then parallel to the space of interpolants is the orthogonal complement. Very good. So what does Bayesian inference do? Bayesian inference says this. You're going to take a prior over your parameters. And here the prior I'm going to take is exactly the prior I would have taken for SGD. I would have sampled from this and done gradient descent. But here I have a different interpretation. You just think of this simple-minded distribution on the W's as giving you a complicated distribution on the thetas. That's how I imagine it. Okay, so whatever this distribution is, though, I've drawn it in this kind of circular way because it is rotationally invariant, right? This first matrix here, because it's a Gaussian matrix, is rotationally invariant. So I have a complicated rotationally invariant distribution on the thetas. That's my prior. And then how do you do learning? Well, I'm going to do learning like this. So the posterior distribution over theta, this is the distribution over theta that you're going to use to make predictions on data points you haven't seen, is the usual thing. You take the prior, you multiply it by the likelihood. This is e to the minus beta times the mean squared error. Okay, you divide by the evidence, you take beta to infinity. Okay, so let me write it in a more human computable way. Okay, so because I'm insisting on interpolating the training data, I'm interested in this kind of over-parameterized interpolating regime. Mathematically speaking, my posterior is just, I take my complicated prior and I restrict it to lie on the space of thetas that fits my data. Okay, and that's my posterior that I'm going to use to sample. Okay, so why do I care about this model? Well, okay, so first of all, this model when L equals 0 is classic, right? If you just have a model that's linear in your parameters W, and the prior is Gaussian, and your likelihood is the mean squared error, the posterior is also Gaussian, and that's like the basis of 99.31% of Bayesian inference in practice. Okay, so one sec. And so this is like a generalization of this model with a more complicated prior. That's kind of how I thought about it. And the fact that this prior is complicated came from the fact that my model wasn't linear in its parameters. Right? The prior was simple in each matrix separately, but the product has a complicated distribution. Yes, please. So right, I make beta go to infinity for two reasons. It depends who you are. If you're my reviewer, I make beta go to infinity because, of course, we fit the data with the neural networks. So I want to study interpolating solutions. So it's like the distribution over the thetas that exactly fit my training data. Okay, but if I'm more honest, I wanted to study it when beta is not equal to infinity, but we couldn't figure out how in this paper. Okay, so both are true. Both are true. Okay, so this is the model. My goal is to understand this posterior distribution. Okay, so here's what I was able to do. Okay, I'm just reminding you what the model is up here. I wrote this paper, okay, a year ago now almost, with my amazing collaborator, Alexander Zlokapa. So what we found was really fun. We found that if you do Bayesian inference in this setting, okay, you do a deep linear network, like I said, you have n samples and you have mean squared error as your log likelihood. You take the zero noise limit, that's this beta goes to infinity thing. You learn the following. So first of all, the posterior distribution is exactly solvable. So that came as a little bit of a shock to us. If you've ever done Bayesian inference, it's pretty rare to have models which are nonlinear in their parameters, but you have a closed form solution for the posterior. Usually you have to do some kind of variational inference or MCMC or some kind of approximation. But here it's actually kind of exactly solvable, which was great. And then with the exact solutions, we could take all our large parameters to infinity. Okay, it was like all of our dreams come true. And I'll show you a picture of this, but I wanted to write it in words first. Here's basically what we learned. Okay, so we take the number of samples, the width, the depth to infinity. So the posterior is determined by the following things. So it depends on the data through the norm of the minimal norm interpolar, and this limiting ratio of the number of samples to the number of features that you observe. And then there's two structural parameters about the neural network that matter. So L over N appears again. Okay, so for general widths, it's the sum of the reciprocals of the widths. And then the number of samples times L over N appears. That was new. We didn't know at least that was going to be the answer. And it plays the role, as I'll explain in just a moment on the next slide, of the effective depth of the posterior. And that's all the answer depends on basically these four numbers. So it's kind of cool. So rather than talking through it, let me just show you the picture. Okay, so the setting is like this. I take little n and capital N to infinity. L can go to infinity if it wants or not. It doesn't actually matter. Okay, and the point is that this ratio converges to what I'll call lambda, and L over N converges to gamma. Okay, so the first place I'll start is the kernel regime. So it turns out that if the width grows faster than the number of samples times the depth, it didn't matter that you had a nonlinear neural network. You get exactly the same posterior as if you had zero hidden layers. Okay, just a linear model. So that's why I call it the kernel regime. So this is kind of the remnant of the NTK regime up here. Then, okay, if you're sort of more physicsy, there's a weakly coupled phase where you have a one parameter family of posteriors, which is just described by this parameter lambda. And then the statistics of the training data, which I mentioned. Okay, so you get this interesting family of posteriors. They depend on lambda and the statistics of the data. And the coolest thing about them, okay, from my point of view, other than they're completely explicit, is we can actually calculate the derivative of the evidence of the partition function, give the denominator in your Bayesian inference with respect to lambda, and you find that the derivative is always strictly positive. So okay, for people who don't do Bayesian stuff, if you have two different models as a Bayesian and they fit the data equally well, you don't equally prefer the models. You prefer the simpler model. And the way the Bayesian makes that precise, at least one way, is you prefer the model with the bigger evidence. So you want to maximize the evidence. And so this was like, at least for me, the first theorem I know of, which gives an exact situation in which deeper is always better. Okay, the evidence always increases with respect to this effective depth lambda. So that's cool. So that motivates you to study networks that are deeper in this effective sense. And you get a second phase of this kind of phase diagram, which you can think of as a strongly coupled phase, if that means anything to you, where now lambda is equal to infinity everywhere, and now gamma goes from 0 to infinity. And there's an interesting phase transition that occurs. So what happens is, here the posterior distribution is the same everywhere. It's actually independent of gamma, and it's the unique posterior that maximizes the evidence. So from the point of view of the posterior, you're happy to maximize the evidence. But although the posterior is the same, actually the evidence is not the same. So the posterior is the same posterior you would have gotten by maximizing the evidence, but actually it doesn't always come from maximizing the evidence. There are many ways to get this posterior. And there's like this explicit function of the training data that tells you what the aspect ratio L over N should have been if your goal in life was to maximize the evidence of your model. Okay, so I thought this was kind of neat because this is much more complicated than I would have thought for Bayesian inference with these linear networks. But this is basically the complete picture for what's going on. Okay, so again, let me just stop for a second and see if there are comments or questions.
One clarification. Calligraphic D here is a finite, like in training data.
No.
Okay.
So I write it this way, but like I said in the previous slide, what you do is you take a sequence of data generating processes, the input dimension, everything is going to infinity.
Okay.
And all you need to know what is the limit of the norm of the minimal norm interpolant. Typically that converges to a constant. That's in most kind of generative models. And you need to know the limit of little n divided by capital and not the proportion of directions you observe. So when I write that D, I mean it depends explicitly on those.
Right.
Yeah. Yeah, thanks for the question. Yeah. So, sorry, can you say, I just can't hear you. Yeah, so okay. The short answer is here the performance is constant because you have the same posterior. The performance doesn't know about the evidence at all. Okay, here the posterior changes as a function of lambda. But the thing is, the Bayesian, at least from my point of view, Bayesian inference is not about maximizing the generalization error. It's not like such a natural thing in the Bayesian world. And you can certainly calculate the generalization error because everything is completely explicit and depends on the norm or the minimal norm interpolant, the number of directions you see. So, and then depending on what you plug in, sometimes deeper is better from the point of view of generalization, and sometimes it isn't. And so that's why this is like a different sense of deeper is better. So it's more like deeper is simpler or something like that. Yeah. Okay, very good. So this was like a year ago. Okay, and my daughter was born like a year ago. So of course I've had nothing to do other than research, right? Isn't that how it works? That's not true. Actually, what it means is I just haven't slept much. So actually it's hard to know if I've had more or less research time. Okay, so what I thought I would do is two things. Let me see how much time I have actually. Okay, yeah. I'm gonna prove to you, okay, in some sense of the word proof, that this model I showed you is exactly solvable. I'm gonna write down the posterior for you, and then I'll briefly tell you about a much more recent paper, which we finished not too long ago, where we do the same thing for Bayesian inference with nonlinear networks. Okay, we can go beyond the linear case, we just can't say quite as much. Okay, so the theorem goes like this. So to characterize the posterior distribution, what I'm going to do is I'm going to tell you what its characteristic function is. Okay, so this means you sample theta from the posterior, and then you write down z of t for the characteristic function that you get. Okay, so under the posterior, the distribution of theta has two components. Okay, so there's the component that's parallel to your training data, which of course is the minimal norm interpolant because you have to fit the training data. Okay, and then there's the component of theta, which is the projection onto the orthogonal complement of the training data. So it's just the natural decomposition of theta that comes from the picture that we had before. Okay, and you get the following formula. Okay, so you either hate it or love it. I, of course, love it, but I feel like it's okay to hate it too. So z of t is written explicitly in terms of these special functions called Meyer G functions. I'll remind you what they are in just a second. But here's what it is. Okay, there's a prefactor, which basically the key point of the prefactor other than the numerical constants is this. This is just saying, this is the characteristic function of the delta function at theta is equal to theta star. Okay, this is just saying that the projection of theta onto the span of the data is the minimal norm interpolant. And the rest of it depends only on t perp, which is kind of the components of t that are dual to the theta perp directions. Can you get this sum? You get a sum over all k of this t perp squared to the k with a constant, and then you get this special function g. Okay, so what's the point of this sum? The point is that, you know, if you want to know things like moments of your distribution, what you do is you differentiate with respect to t, and then you set t equal to 0. Okay, and all the dependence on t is in this prefactor. The derivatives are easy. This is just the constants. Okay, they're complicated, but there's no need to differentiate them. Okay, so what the heck are these constants? So m is just, okay, it's a product of 2 sigma squared over NL. Sigma squared is the variance of the prior that I put in each weight matrix. And this GL is what's called a Meyer G function. Okay, so this is a special function. It's a meromorphic function of one complex variable. And it has, with a subscript L here, it has L hyperparameters. And it's this contour integral. Okay, you integrate over it's like a melon transform, basically. You integrate over the imaginary axis in the complex plane. This z to the s times a product of some gamma functions shifted by the parameters. Okay, it's like, for me, you know, you started with a problem that had a growing number of integrals. That's how the posterior is. You have to integrate out all the weights. And I've reduced it to a problem that ultimately just has one integral. If I really wanted to, I could bring the sum under the integral sign, and I'd have one complicated integral to calculate. So that's what it means for me to solve a problem. You write down one integral in the complex plane, or it's fine if there's a finite number of integrals too. And then you analyze it by stationary phase or steepest descent, or whatever you like to call it. Okay, so this is kind of what the actual theorem looks like. I feel like I owe it to the audience to show the actual formula, so you have a sense of what it is we did. So let me see. Do I have 5 minutes?
Yeah.
Okay, I'll take.
If you can do 4, we'll do 1 or 2.
Great, I'll try to take 3 minutes, maybe 2,
Sure.
maybe 2.5. Okay, so finally, so scaling limit version 4. Okay, I couldn't help myself. I had to add a slide about it. Okay, so of course, what I hated about the previous results is the deep linear thing. I mean, it's interesting because it's nonlinear in the parameters. That's why I thought it was an interesting model, but it's linear in the x's, so you can only ever learn a linear data generating process in x. So that's okay, but not great. So what we did is we studied what are called shaped networks. So it turns out, so here I call the nonlinearity phi for reasons that pass understanding. Okay, so if you want to take the infinite depth limit, what people realized a couple of years ago now is you can't just take a fixed nonlinearity like ReLU or tanh or something like that. And the reason is the prior distribution you get will be degenerate. Okay, the right thing to do is you need to be in every layer close to the identity. How close? Roughly 1 over L close. Okay, so this is kind of the simplest nonlinearity, which is not the identity. And it just has this constant C here, which is like the nonlinearity strength. And in every layer, you're 1 over L away from the identity, but you have L layers. And what happens is you're order 1 away from the deep linear network under the prior. That's how the scale. Okay, so we wanted to understand Bayesian inference in this setting. And here's what we found. Okay, exactly same setup. So actually, we can do any temperature. We don't have to take beta to 0 here. So my referee is happy. Okay, take n samples, mean squared error, log likelihood. So what we found is that at least we don't know how to exactly solve this model. We don't have quite such a nice formula as the deep linear case, but we can solve it perturbatively. So what that means is you take the number of samples, the width, and the depth to infinity, and you can basically expand the answer in powers of 1 over n. Okay, and you can compute the 1 over n corrections in principle to any order that you like. Okay, that's what I mean by perturbatively solvable. So that's less than we had before, but the model's much harder. Okay, and then we found the following thing. So first of all, the kernel regime turns out to be the same for the nonlinear networks. Okay, so you get Bayesian inference with a kernel if and only if this effective depth parameter, little n times capital L over big N goes to 0. So again, this is when you calculate the first order correction in 1 over n, you see that it scales like the number of samples times the depth. Okay, and now if this thing goes to 0, then this psi here still plays a role. And the psi actually controls the kernel that you get. You get a 1 parameter family of kernel methods that depend on psi. And it turns out that psi plays the role of the kind of curvature of the manifold into which you embed the data under your feature map. Okay, so just ask me about it later if you're interested. But this is actually like by far the most kind of concrete interpretation of the nonlinearity at large depth that I've ever seen. I didn't know anything like this, at least before. So that's cool. So you get this kernel method. And then what we do is we compute the 1 over n correction to this kernel method. So to first order in 1 over n, the correction looks like little n times capital N over big N. And what we find is you can interpret the posterior as being exactly what would happen if you had what we call a data-dependent kernel method. Basically, you take the kernel that you would have gotten when this effective depth went to 0, and you deform it in a way that is sensitive to the sample covariance matrix of the data that you observe. Okay, so that's not a kernel method at all. It's a data-dependent kernel method. It's a little bit like doing empirical Bayes. Like you observe your data, and then you choose your linear model based on what you observe. And the model does something specific. We have an exact formula for it. I just didn't include it here because it's like didn't quite fit here. It would take longer to explain. Okay, but I was really happy that there's this model. Like the neural network is nonlinear. You can take the depth, the width, the input dimension, the number of samples, everything to infinity. You can get very concrete answers to come out. And it's just kind of, for me at least, the starting point of understanding what these models are going to do and what learning looks like. Now, like I said, trying to redo this for stochastic gradient descent rather than Bayesian inference. And I think it's all going to be doable. And I think this is still kind of the right variable to study that controls the effective depth and so on. Okay, so that was my promised 2.5, i.e. 5 minutes.
Times 2, yes.
Yes.
All right. Awesome. Thank you, Boris. We already a couple questions throughout the talk, but maybe we can take 1 minute or two if there are any quick questions from the audience.
So 2 or 4, am I?
We'll
I'm just
see.
kidding.
What is so peculiar about TQ?
Right. So what it turns out is the following. So the general papers, which I just didn't have time to review, if you have an odd function, a general odd nonlinearity, what you're supposed to do to shape it, if you want it to give a reasonable limit at large L, is you multiply it on the outside by square root of L, and you rescale t by 1 over square root of L. So the linear term will look like this. The cubic term will have a 1 over L correction, and you'll have other corrections, but they actually don't matter in the large L limit. So this is basically the answer when you reshape any odd activation. But there's a different reshaping if you want to reshape the ReLU. You have a 1 over square root of L correction to the ReLU. We didn't do that case. But those are kind of, it seems, the two natural ways to study large L limits of these fully connected networks. You have to do these kind of reshapings.
And what does it mean to set the curvature of a feature base?
Yes, so here, okay, I just didn't have time to say this, but basically what happens is when you ask, okay, you get some kernel method, what's the feature map? The feature map basically does this, it takes the x's that you started with, and if psi is positive, it embeds them into a hyperbola of curvature psi. And then you run a standard kernel method on top of that. If psi is negative, it embeds them into a hemisphere of curvature psi, and you run the kernel method on top of that. So it's quite literally like, there's a nice simple geometric interpretation for the feature map that you end up getting.
What was shape network?
Yeah, so shaping, so okay. The history is like this. People study these fully connected networks, and they wanted to understand what happens when the depth is big. And what they found is if you have a fixed nonlinearity that's not the identity, like ReLU, you get something very degenerate. Like any two different inputs are going to map to the same output. So then they realized that what you have to do, and that's what they called it, they said you have to reshape the nonlinearity. So they want to make it close to the identity in each layer. So this shaping just means you massage the nonlinearity to look close to linear in each layer, so that when L is large, you still get a non-degenerate distribution. It's just the word that they used that I sort of, okay, I took it because that's how people describe it, yeah.
Okay, maybe in the interest of time, let's take the rest of the questions offline and join me in thanking Boris once again. We could have the next speaker, please. I'm very sad because I didn't get to ask mine. So,
Fair enough.
you can just connect to.
So I'm not gonna share my screen. Just gonna share my screen through Zoom. Yes. ID. It's drawing. Yeah, it's drawing. 957 440 9132. Yes. And the long down connect. Yes. 626 050. I think you can turn off the video. Yes. So we have still video. Yes. Oh, okay. Perfect. You know, about it to share. Spoiler. Spoiler.
That's it.
Okay.
Okay, so next up, right before we go to the next coffee break, is Simon Mombari, who's going to tell us that privacy comes for free all the way from Austria. Welcome.
So thank you. Thank you everyone for being here. Thank you to the organizers for setting up this great conference. I am Simone Bombari. I'm a PhD student at ISTA, and this joint work with my advisor, Marco Mondelli. So this is a quick agenda. Okay, let's see this of this work. In particular, I'm not gonna assume much in this talk, so I'm gonna present what do I mean by privacy. I'm gonna introduce differential privacy. I'm gonna introduce notions like the cost of privacy and the random features models. These are the technical settings you're gonna need in this talk. And then at that point, I will be ready to present the main result. And that hopefully is gonna explain the keywords in the title. And then if time permits, I'm also gonna probably fly a bit on the proof ideas, if anyone's interested, and then some numerical evidence and conclusions. So first of all, what is privacy? And this can be a relatively vague concept, and probably depending on the setting, this assumes different meanings. But let's go through this via an example. You can imagine that a ML engineer of yours is asking you for your photos to improve their services. So you take a, let's say, sensitive photo of yours, you give it to your friend, and this friend uses this photo to train a model and obtain some weights, theta star. Then your friend deletes your photo, and hopefully everything is going to be all right. But it turns out that somebody, maybe with the knowledge of the final weights of the model, might be able to reconstruct via some magic the original photo. And this might seem too magic to be real, but it's actually real, and it has been shown both in natural language processing and also computer vision. This doesn't make you happy, and ideally your friend, so the ML engineer at point number 2, should implement a magical algorithm such that there is a formal guarantee such that step number 3 is not possible. So how do we do this? We do this via differential privacy. So allow me to go through the definition. An algorithm satisfies epsilon delta differential privacy. Epsilon and delta are going to be 2 positive numbers. If for any pair of adjacent datasets, this means that D and D prime differ only on one sample, for example, your photo. And for any subset of the parameter space, so P is the number of parameters, we have this inequality in probability. So the first time I saw this was a bit confusing. So let's maybe go through some cases for the people that have never seen this so far. So if you set epsilon delta equal to 0, you easily see that this means that the outputs of the algorithms are going to be identical. And this really represents privacy because it means that if your photo is or is not in the training set, nothing is going to change. So practically, the algorithm is not using any information about your photo. So there is no way at step number 3, someone is going to be able to retrieve information from this. On the other edge, if we set epsilon to plus infinity or delta equal to 1, this inequality becomes trivial. So we're not enforcing anything in our algorithm. And in practice, we're going to be somewhere in the middle. So during this talk, we're going to assume epsilon of constant order. I think it's helpful to imagine it being equal to 1, let's say. And delta is going to be much smaller than 1 over n. This in practice is what's considered giving meaningful privacy guarantees.
Sorry, I
yes?
see it immediately, but what is the randomness of?
That's a great question. Randomness of the algorithm. In particular, not the data set. So you're not going to say, I'm going to sample data because that's very bad. But that's a great question. I forgot. Please interrupt me if anything is unclear or bad. So how do we do this? I would really love to implement these magical algorithms that implement differential privacy needs. So let's go through first gradient descent. This is probably something everyone agrees on in this room. And the process is very standard. For every input-output pair, we compute the per sample gradient. Then we aggregate these gradients. We take the mean, and then we do a gradient descent. This way, I'm also implicitly defining some notation. For differential privacy, we need something very similar, but we add also some tweaks. So as you can see, we are, again, computing the per sample gradients, but before aggregating them, we're clipping them. So there is a hyperparameter, which is the clipping constant, that is telling you, okay, look at all your gradients of your data set. And if any of them is too large in L2 norm, then you're going to have to rescale it in a way that the L2 norm of this gradient is going to be at most the clipping constant, this magical number you're going to put in your algorithm. Once you do this, you can aggregate your gradients, and after that, you can update your model with a gradient descent, and you're going to also add some standard Gaussian noise to it. Every time you're going to sample it at every iteration, and notice that this noise is proportional to the clipping constant itself, and also proportional to this noise scale, noise multiplier, which is a hyperparameter of the model. This might seem a bit random, especially if this is the first time you see this algorithm, but people before us proved that if you set the noise scale large enough, and it gets larger as epsilon becomes smaller, because smaller epsilon means more privacy, so more noise to perturb your algorithm more, then dPGD will be epsilon delta differentially. Okay? This is great. So eventually now we can take all our algorithms we have at home and just add a couple of lines of code and make them private. Why not? And the reason why not is that privacy comes with a cost. So I would ask you to focus on the blue line that comes from this paper, which at least in 2022 was giving baselines for CFAR10 with differential privacy. You see that, for example, for epsilon equal to 4, the test accuracy of CFAR10 is below 75%, which is way below what you would get if you're not using privacy. And you see that this test accuracy goes smaller and smaller as epsilon becomes smaller, so more privacy, and gets higher if epsilon becomes larger, so less privacy. There is a clear trade-off between these two things. And from an algorithmic perspective, why is this the case? The case is really about the tweaks we implemented in. So we said, we're doing some clipping, we're doing some noising, and implicitly we're also doing some early stopping, because fixing a noise and a clipping constant, you're also fixing the number of training iterations you're allowed to go through during your algorithm. So you might think, okay, I'm going to set the clipping constant very large, so I'm not going to clip my gradients. I'm going to set the noise multiplier very small, but that generally is going to imply that you can train for only very few iterations, so you're not going to be able to learn. Yes?
Explain what is the intuition between the connection between clipping gradients and ensuring privacy?
Okay, this is a great question. I'm going to repeat it, so just to make sure I have it. What's the intuition between clipping a individual gradient and achieving privacy? So imagine we have a data set with an image, which is an outlier, like a white tiger. We have only one. And if you're applying a differentially private algorithm, this algorithm cannot learn this image, because the algorithm should be blind with respect to outliers. The fact that this image is so different from the others is going to, during the training dynamics, really give strong signals to the model. So eventually this gradient is going to increase in size. But we do not want this. We want to limit the amount of information a single sample is delivering to the model. And this in some sense is also very similar to early stopping. We do not want images to send too many informations to the model. Does this reply your question? Okay. So I know that early stopping also some form of noise and gradient sometimes is associated with implicit regularization and beneficial effects for the generalization of your algorithms, but I would really ask you to not have this perspective during this talk. In particular, these three things are actually problems. So if you're an ML engineer and you want to achieve the best performances possible for a fixed amount of epsilon, there will be a lot of balancing between these three quantities. And it will be of key importance really picking the optimal hyperparameter point in this space. So in some sense, we need to defeat these guys. This is the perspective of the ML engineer, but if maybe you're a theoretician, then maybe you're interested in more abstract question. You're interested in fundamentally this trade-off. What does that mean? So, for example, we can define RP as the difference between the test loss of a private model, so theta p, minus the test loss of a non-private baseline, theta star. So if this difference is very high, this means that we're losing a lot of performances implementing privacy. If this difference is very small, it means that private solutions and non-private solutions perform more or less the same. And these trade-offs will most likely depend on epsilon, so how much privacy actually you need, the number of training samples, and the number of parameters of your model. And there are a lot of results in many different settings from the last decade. And there are upper bounds, lower bounds, both on generalization error and also empirical risk. It turns out that overparameterization brings a curse with it. So overparameterization is the regime where we have more parameters than training samples. And for example, what we can do is taking these bounds and applying them black box to a very easy and simple deep learning-like model, like a random features model, like a two-layer neural network where we're only training on the second layer. And if we do this, we see that the guarantees on the excess population risks these bounds give for epsilon equal, let's say, to 1, they're telling you that the success population risk is big O of 1. This is telling you that your model is going to be at least as good as a model that constantly outputs 0, because this is chance level. The loss is a constant that we cannot track. So I would call this a lack of a theoretical result, and this lack of theoretical results also generated a common wisdom in the community. I put these 2 references, but this is something that vaguely sometimes appear in papers on differential privacy, is that overparameterization is inherently bad for private learning. And the intuition is sometimes motivated by the fact that since we're adding noise at every iteration, this noise in norm increases, L2 norm, increases if the parameter space increases. So it feels that we're adding more noise, we're perturbing more, and perturbing more means less utility. And this consequently motivated researchers to develop algorithms, maybe in lower dimensional spaces, or maybe trying to inject noise in a non-isotropic way, again, to try to limit the effective dimension of the training of the learning algorithms. So the overparameterized regime also in the non-private setting made researchers think a lot and discuss a lot in the last few years, in particular the fact that large neural networks, very overparameterized networks, work very well in practice, seems in apparent contradiction with the standard classical bias variance trade-off. And these I'm only putting one reference, but there is really a lot of works. And in the last few years, concepts like interpolation threshold, double descent, or benign overfitting made people more comfortable and aware of the fact that using larger models can be beneficial, even without explicit regularization. In the private settings instead, things seem to not be already on the right side of these double descendants. Things seems a bit more pessimistic towards the number of parameters. So I would want to argue this. I'm going to elaborate a bit more later. So let's just run a simple experiment. The experiment is just training a 2-layer neural network on MNIST, very easy task, with differentially private gradient descent. I'm going to increase the width every time, and I'm going to plot the test accuracy as the width grows larger and larger and larger. Even if it's true that overparameterization is inherently bad for private learning, I would expect at some point the performances to go down, to degenerate. But this is not what we see. This again is a very simple experiment. This is only on MNIST, 2-layers neural network, but this phenomenon doesn't happen. It feels that it's really plateauing, and it keeps going also when the number of parameters is almost 10 to the 7, which should be order of magnitude more than MNIST dataset size. And of course, I'm not the first person that says this. So there are actually papers doing real experiments at scale with ImageNet and CFAR, like the paper I also showed you before, that finds their baselines with bigger ResNets rather than 16.4. They use 44, and they here find the best performances, and they achieve the state of the art with these models. There are other papers that found these, for example, in fine-tuning, but still, there really feels that there is some phenomenology in deep learning that cannot really be described by the current theoretical results. So the feeling is that maybe there should be a theoretical attack that would allow us to understand better the phenomenology, and in particular, the specific goal of these papers is to provide a non-vacuous upper bound on the excess population risk in overparameterized regime. Yes?
Does this figure tell us that increases
Yes. There is also this in this. So we have epsilon equal to 1, 2, and 4. And the test accuracy is increasing because you're asking for less privacy. Lower epsilon, more privacy, higher epsilon, less privacy.
This is all different.
Sorry?
This is all different.
This is the PGD. So I'm actually excluding the batching from this study, is always full batch. So full batch GD, and there is the least amount of tricks that you can think of. This is the easiest experiment probably you can run. Okay, yes?
So,
okay, I don't think I heard the last part, but I heard, why didn't I try SGD on this?
So in this way, you check that you get double descent with GD.
Okay, double descent with GD, okay, here, for example, you do not see it, right? Now, sorry? This is the PGD.
say that it's the.
If I use GD on this setting, I would see a little bump. Yes. Is that your, does that reply your question? Yes? You also want it? Sorry, can you?
Yeah, sir.
This is not going to work. This is not going to guarantee you privacy. And this actually matches very well with the initial question. The noise you're adding at every iteration, that's the randomness over which the first inequality for differential privacy is defined. So we really need to add this. Okay. So now the goal of this work is trying to provide a known vacuous upper bound on the excess population risk in the over-parameterized regime. This is also trying to capture a bit better the phenomenology that we see in deep learning. So to do this, we need to define a model. In particular, I'm trying to use the easiest model where I can actually do some math on, because that's as far as I can get for now, almost, which is a random features model. This is a 2-layers neural network. Phi is my activation. Theta are the trainable parameters. And V is a random Gaussian matrix, which I initialized and I'm not going to touch during training. So I'm just going to train theta, and I'm going to train with quadratic loss. The appeal behind the random features model is that it's easy enough so that I can do math on, and is also rich enough such that I can actually explore maybe what overparameterization brings, and something that we can see with more or less overparameterized regime. For example, the random feature model exhibits the double descent. And given this appeal, this model has also been extensively studied the last few years. Now we have a fairly nice understanding of the test error for some data distributions. For example, this staircase-like plot. I'm sorry, probably this cannot be seen, but this is logarithm of n, number of samples, divided by logarithm of d, input dimension. And we see that as n increases, so as we have more samples, the test loss decreases because we're learning more and more parts of the target. Okay, so at this point, let's just run dpgd on this model, and let's see what we get. This is the main result. The main result states the following. Theta star will be the solution of gradient descent. Theta p will be the solution of epsilon delta dp, gradient descent. And for a proper choice of the hyperparameters, so at this moment, I'm still not telling you which hyperparameters, clipping, noise, and early stopping I'm using, we can get this, of course, under some technical conditions and for all sufficiently overparameterized random feature models. This upper bound might not seem super informative, so we're working in this maybe a bit restrictive regime where n is way larger than d, so we're not in the linear regime. In this sense, we are faster than the number of pixels, but it's also not that large. So n is between d and d to the 3 divided by 2. And if you look at this and you set, for example, epsilon equal to 1, you see that all these free terms will vanish. So will be small of 1. So this means that the gap between the non-private solution and the private solution converges to 0. And that's what we mean by privacy for free. And also notice that there is no p in the bound. We only need a lower bound, which is p larger than n squared. I believe this should be p larger than n, but the proof at this moment works like this, and I think probably can get better with some more work. Now, many of you at this point might be suspicious. So, I told you that privacy comes with a cost. So now I'm telling you that privacy can come for free. So there is an intuition behind this, and the intuition is the following. When we look at the test curves of the random feature models, there are some regimes where this test loss plateaus. If the test loss plateaus, means that we have more samples than what we need. So the model is not relying on any individual sample. This means that the model does not look too much at any of these samples. So in some sense, there is a surplus of samples that can be used to learn privacy. And this is the intuition behind privacy for free. And these might still look a bit pathological on the random feature models, but let's look at MNIST, for example. Here I'm plotting the test accuracy with respect to the number of training samples. Gradient descent in blue, so non-private, it increases pretty fast when n is smaller than 1,000. And then it starts plateauing. MNIST is a very easy task. So it feels that we have more training samples than what we actually need to get good enough performances. And notice that as soon as gradient descent starts plateauing, that's the moment where the private performances skyrocket. Because this is the moment where the model is not relying anymore on any individual samples. So we have space to learn private. Yes. Sorry, please go.
So it's a really interesting intuition. So should I think about it somehow like, you know, I have n samples, but I only really need like d or d log d or something to learn the linear thing. So I could just take my samples and just average some. Like just only feed in like d log d samples, which are like averages of the x's.
Exactly.
And that means you can only like recover the x's up to that.
Exactly. So that's probably the perspective of synthetic data sets, where you're changing the data set and then training on top of it. Here is more implicit. And yeah, of course, notice that, you know, for example, in the quadratic regime, this is not true anymore. So, you know, it's really working because we're on a plateau.
But I mean, could I have done that without adding noise? Like imagine I just took my data set and I just replaced every little group of x's by just the average of the x's, the average.
Okay.
And I don't need to know noise, and I can only recover the averages, presumably. So I can only recover the x's up to, I don't know.
Okay, these are very fair concerns, let's say. But for example, if we stick to the definition of differential privacy, that's a probabilistic definition. So there should be some noise sum, right? Because
I'm saying with probability 1.
Probability 1.
All my algorithm sees is the average of some x's. And I can't recover the x's up to the average of a clusters and grid.
The point is that the average is going to depend on every single sample. So if you change one sample a bit, the mean is going to change a bit.
It will change like 1 over d.
1 over d. So
d over
exactly, yeah. So the maybe in the limit this is true, but for any fixed DNN there is going to be a difference. So the probability.
Yeah, but for you, you also have a difference between d.
No, okay. My point is the following. So. Okay, honestly, I think I got the point, but probably it's better. Yeah, of course.
That's really interesting.
There is any other? Yes?
What's your target function?
Okay, the target function in here, no assumption. I use the independence on the label. So label number 3 cannot depend on sample number 5, but in principle can be, and also I'm considering the labels to be bound, so by constants. But I'm not assuming anything on the label. Consider, for example, here, this does not mean that the test error goes to 0. This means that the test error approaches the test error of gradient descent, which in principle might not be 0, like here. Okay, there was him before. Yep.
So here the number of samples is much larger than the
N squared, yes.
So you're on them.
No, number of training parameters, so the width of the random features models.
So P
is larger than N squared. Yes.
So that's how you define it.
No, what I define by the open parameterization is P larger than N. This is what we use for the proofs. Okay. And I believe that I can do proofs better.
And just one quick one. What are the fundamental trade-offs between that it goes for any model between privacy and
yes. So for example, now here I'm only talking about upper bounds on the excess population risk, but there are also papers that study the lower bounds. And that depends on the setting. So all these papers I showed before, it was constrained, strongly convex, linear regression. That really depends on the setting, but there are lower bounds, yes. Yes?
What's your assumption?
You got it. So in this case, we actually make very strong assumption on the activation, which means 0th and 2nd order of the Hermite polynomial, Hermite coefficient of the activation is 0. And you might not believe me, but I think it's matter of, it's technical. It's a matter of making the proofs a bit easier. So the intuition is that this, for example, this does not rely on anything like degenerate like this on the activation, probably requires only L2 integrable. And the staircase is the qualitatively phenomenology we're looking for to have this. But yeah, if you go through the lemmas, you really see that, you know, there are some terms which I'm very annoyed to deal with. So I just set the Hermite polynomial to 0. Okay, how much time do I have?
1 minute.
1 minute.
So maybe take another 2, but.
Okay, thank you. So actually, this is it. The point is that I had the proof ideas, which I said I would have been super happy to discuss with you if I had the time, but I don't. So I'm going to fly over them, just more like throwing keywords. And if you love the keywords, please stop me later. I have the poster downstairs so we can actually have fun with the proofs, which is probably 99% of the time I spent on this project. So we can discuss with it. So the idea is the following. I want to write DPGD as a stochastic differential equation. So learning rate very small, number of iteration very large. This I cannot do because I cannot send to the limit the clipping step. So I define a surrogate loss, which is thus the Hoover loss. So it's quadratic at the beginning and then continues linearly. This proposition tells you, running this on quadratic loss with clipping is equivalent of running the same algorithm on the surrogate loss without the clipping step. At this point, I can write the Tth iteration in this way. This is just the Euler-Maruyama discretization of the stochastic differential equation. At this point, I can just compare these two continuous algorithms where I can do some math on. And now it's about, again, understanding this yellow, blue, and red that are going to be eventually the killers of my utility. How do we deal with the clipping constant? It's actually not the updated version of the slides. How do we deal with the clipping constant? I need to set it to some value, which will be this one, which is just large enough such that I'm never going to hit the boundary where these two losses differ. So I'm really at the edge where using quadratic loss or clipped loss are the same. But notice that I cannot just solve this problem taking this clipping constant too large, because in that case, the noise I have to add is going to kill me. So this has to be done pretty tightly. Once I have this, I can look at the noise part, which is a bit easier because it's just standard concentration inequality. And for the early stop, I just rely on the fact that there is a spectral gap in this setting, so I can early stop before the training loss goes to 0, but at the moment where the test loss is already at the point I like. So I put everything together, and the results gets easy. So again, since I'm already probably above the 2 minutes, just some plots. This is random features models. This is neural network with MNIST. Again, very toyish, but hyperparameter space really look alike. So there is a bit the capturing of the phenomenology we're looking for. Our proofs really happen at the edge of this yellow region, which is the good hyperparameter zone to get the utility. But also notice that aggressive clipping, so using smaller and smaller and smaller clipping constant, actually works just fine. I'm sorry, this was very confusing, but please stop me during the coffee break. Some conclusions. Now, I hope the title of the talk is a bit more reasonable. I would really want you to bring home this fact, which is that overparameterization is not at odds with private learning. This, I think, is the main message of this talk. And this might look a bit rhetorical, but actually we believe our results to be a bit more general. So, for example, every level of the staircase and every, for example, kernel problem where we have some form of concentrations. This probably happens also with NTK and similar random kernels of this kind. And ideas for future work, if anyone is interested, the first is using batching. So batched learning, batched DPGD is actually what's used a lot in practice, even though they use way larger batch sizes than in their own private case, generally. Learning features privately. A lot of people are interested in features. So I'm actually very curious, fundamental limits on learning features in a private sense. And something that probably I also really like is getting real insights, not in random feature models, on hyperparameter optimization. For example, doing optimization on smaller models and then using larger models and being quicker on knowing what are the optimal hyperparameters. Remember, this is a very expensive way of training neural networks, so these can actually be interesting also for a wider audience. So let me thank again my advisor, which is a co-author of this work, and thank you, and sorry for being over time.
Just perfectly on time because it's exactly half an hour since you began, so it's perfectly on time. There's been a lot of questions. I would encourage you to continue the discussion offline, and then we'll be here in 25 minutes for the last session of today's session. All right, please join me in thanking.
Thank you. Thank you. Thank you. Good job. I mean, over time, a lot of ideas, unfortunately. Oh, really great job. Thank you.
Yeah, I'm just saying, yes, I was saying. Quite a bit. Next is not you, just saying. Oh, thanks.
Yes.
You're not just messing with
No.
Those been my dream, just to say. Next speaker needs no introduction, then just sit down. Let it be. Yeah. It was very tempting to do that when I was introducing the head of the department and the founder of the institute to the institute. That would have been, yeah. It's like, if you don't know who this dude is, just get it. What's his your
So I did call it. I think the moment you start, people will trickle.
Okay.
I think it'd be, yeah.
All right, to stay on time, let's get started. All right. So our next speaker is Cameron Harris, who will be telling us about something I'm very curious to know what it means.
What does it mean?
Stochastic rainbow network. So
okay,
buckle up.
Thanks for hanging on, everybody. Last two talks. Great. So the questions that motivate my research, right, is I'm actually both an applied mathematician and a neuroscientist. So I'm interested in kind of the structure of beyond just artificial networks, also the brain, and how artificial networks are similar or different from them as well. So like in real brains, we've seen for a long time that there's these structures like layers. We've known about that from just observing what the brains look like. You also have interesting kind of architectures that you don't see maybe in artificial networks, at least not often, like rings that are building in some kind of attractor. And biology builds this, just from the genome, right? And it's not necessarily learned through like a supervised process. Whereas in artificial networks, you have all the architectures that we know of, but also we have very strange architectures, like in this paper, just randomly wired convolutional networks were shown to perform pretty much as well as any nice architecture that seems principled. So something is different there as well. So the stuff I'm going to tell you about is all based on random networks, and it's definitely a simplifying assumption. It's something we do to make theory happen, but and these randomized networks, like random feature networks, they go way back, even in the 50s. So maybe if Boris was saying, right, that in the 50s we could just do linear regression. Well, actually, like the first artificial networks were in the 50s, and the perceptron was originally proposed actually to have a random feature layer in the beginning. So that was built in those very first networks. And then in recurrent contexts, these have been used in a lot of different neuroscience projects. And these kind of random feature models actually can explain a lot of interesting phenomena, even though they don't capture feature learning. Performance at or near initialization, going back to the 90s, implicit bias. So I think this is interesting. So the architecture you choose actually affects, if you're in the kernel limit, the kernel that you're working with. So it does actually tell you something about why a certain architecture is useful for a certain learning problem. And but now I know we're fitting, so we saw the double descent curves last time. So what I am moving towards, though, is all of these results assume that the weights in your network are completely unstructured. And what I mean is they almost all assume that you're drawing your weight vectors from an IID Gaussian with a spherical covariance. So there's zero structure in the actual weight vectors themselves. And we know that the structure of the weights matters, obviously, right? When features are learned, the weights change, and that is what makes the networks good for a certain problem. So what I'm going to tell you about is kind of a couple of things we've been building towards structured random, what I call structured random feature models. Okay, so how this is set up. So this goes back to some work from a couple of years ago with a student from the University of Washington that I worked with. And in the most basic form, a structured random feature model, in my definition, is just, okay, I've got a two-layer neural network here, in this case. I've got these weights from the input to a hidden layer, and I'm going to draw them from some distribution, but I'm going to freeze them at initialization. So really, I'm studying a neural network at initialization. And then I'm allowed to learn this readout set of weights. Right? So I'm in this kernel regime if I make this network very wide. And if you're thinking about learning from a time series, maybe my inputs here is a vector of some variables measured across time. Or if I'm thinking about machine learning and MNIST, my image is just flattened into a vector, right? So if I have no structure in my weights, all I'm seeing is white noise in both settings, right? So I can plot you the time series of my W of t there, it's white noise. Same as if it's a spatial thing, my spatial filter is just white noise, right? Nothing interesting. Whereas you can actually build models of random weights where you have structure, like I'm selective to certain frequencies, spatial frequencies, temporal frequencies, maybe localized in time. So the way we went about doing this is just a nice generalization of weights everybody's been studying forever. It's just now I'm going to just build in a covariance matrix to my random weights. So I call this a structured covariance. So in all the models I'm going to be telling you about, all of my weights are drawn from a Gaussian with zero mean and a covariance C, which is a nice, builds on everything. And we were also thinking about neuroscience. So it turns out if you look at the way that neurons respond to a visual stimulus, by the way, please raise your hand if I'm confusing you or you want to ask something. The way the neurons respond to spatial stimuli is we call them these receptive fields, and that you can think of as a proxy for the optimal input or the weight, right? So we had a large data set of these, and we basically modeled their covariance, and we could sample them. We can control from a nice model with two parameters, kind of the size of this receptive field and the spatial frequency in this first study. And then here's two samples from that Gaussian process. They're maybe a little noisier, a little less wavelet-like than the true receptive fields in this case. Okay, well, if you cook these into your network at initialization and just learn the readout, and you do this very basic task, MNIST, right? You can see that it gives you quite good performance, even with a very few features. And then that is much better than, say, using a weight covariance that is completely unstructured. That's a different cursor, which is this. I want to move this cursor. This orange line. Right? So this is just a pure random feature network learning, and I'm seeing that I'm doing much better with this V1 inspired weights than not. And if I pick my weight covariance wrong, obviously, it could be bad for me and make it even worse for this problem. That's what incompatible is. And in this setting, we actually showed too that with these structured random features, if you use them as your initialization and then you do actually learn the weights, it's kind of like a warm start for your SUD process. So here you're seeing that actually I can train better in this MNIST task. I get to a lower loss much more quickly if I pick the right weights. Question.
Again, how do you see?
In this setting, we had like a 2-parameter function that was our covariance function that we just fit to the neural data in this setting. Yeah. From biology. Yeah, from a mouse's visual receptive fields. Yeah. Yeah.
But I'm confused as to what that means, because here we're talking about any neural network with any dimension of the weights, and therefore the variance matrix might just change completely. So I don't know what that means.
Well, if you hang tight, I'm eventually gonna learn the covariance matrix through backpropagation. So you can think about, this whole like structure random feature model. If you're not interested in, if you just want to study GNNs, you can think about it as a model for the network after it's been trained. So it's learned some features. The weights are now no longer what you initialize with. Okay. And now I'm trying to understand the structure in those features, and I could, as a simple thing, just kind of look at the correlation matrix or the covariance matrix of those features, those weights. But yeah, in general, this is going to actually, well, you'll see. It's not just spatial; it's also channels, right? So I don't think I need to go through this very much, but and obviously the kernel approximation is not great if you're doing feature learning, right? It doesn't capture that, but I think it's interesting too because it does show that structural bias. So as long as our weights are IID random, in very much general settings, they're going to converge to some deterministic function as the width goes to infinity. So that's what people call kernels or neural network, Gaussian process kernel. So, okay, here's my one slide of more math, and I'm not going to call it a proof or a theorem because it's fairly basic, but that's kind of what I do. So I've assumed my weights are random vectors from this Gaussian process, right? So thing we should do is diagonalize the covariance matrix, right? So the covariance is giving this expectation, and it has some orthogonal eigenvectors, which I call U, and it has an set of eigenvalues, which are all positive, so I could call them lambda squared, because they're positive, I can take their square root. So, okay, that means that if I want to sample my random vector W, what I can do is actually sample from a spherical Gaussian, scale the entries with my eigenvalues, and then rotate. So this is what you do when you sample from one of these multivariate Gaussians. This is how you generate it, right? People are probably familiar with this. So if I'm a neuron in this network and I'm seeing an input X, that's the same as actually taking my input X, putting it in the eigenbasis of this covariance matrix, and then weighting the different eigenfunctions or the eigenvectors by different amounts by this lambda, and then doing a random projection with a spherical Gaussian, right? So this is just linear equivalence. There's nothing fancy. And that whole transformation by U and lambda is non-random, right? The only randomness is in G. So I thought that was kind of interesting, and these kernels will change in that setting. I call this a structured kernel. So it changes the data, the input data. So why is this useful? Well, the way I think about it is, say I'm trying to learn to separate two different types of data. One is just white noise, and the other one is noise of with a hidden signal inside. So there's a hidden frequency in my signal that's got higher power. So I have these two classes. So there's one relevant component in my time series, and then I've got all these irrelevant components. So you have this hidden thing to find. So the optimal classifier here is to draw a circle, right, and separate these things out. Okay, so maybe there's some target function that looks like a quadratic that gives me this circle, right? Well, you can show, if you go through the math of that kernel, basically what it's doing, right, when you pass through that that eigenbasis and you separate out, you filter with those eigenvalues, is it's reducing the dimensionality of the problem. So as long as you know what frequencies to look for, you're kind of reducing the dimensionality, and so you're making the problem exponentially easier to solve by working in lower dimensions. So maybe it's sort of obvious, right? Like if you're doing network learning and feature learning, you're looking for certain subspaces of low dimensionality, and that's why neural networks are getting you somewhere. Any questions about this at this point? Okay, so what is this rainbow thing anyway? So that was just the kind of the warm up. So obviously this is DeepMath, and so far I showed you a shallow network. So I wanted to move towards multi-layer deeper networks. And I have kind of projects playing with this in unsupervised and compressive sensing type settings as well, but I'm not going to tell you about that. But these ideas do work there as well. So we have these 2 workshop papers. And most of this work, the simulations and stuff, were done by my student Vivian, who's actually an undergrad. And then this other student, Wawiz. But yeah, Vivian is looking for PhD programs. So just a plug there. Okay, so what we did is we decided, okay, so these structured random features, it's interesting maybe theoretically, but like you can't get them to perform very well unless you know what the covariance should be, right? So we thought in deep networks, we don't really know what it should be, so let's just learn it. So here's the idea, right? So if I'm at some layer and I'm looking at the input, and I'm going to think about convolutional networks now. So my convolution is going to see a little patch of my image, and I'm going to assume that there's n channels in that patch. I drew that as having many channels because I'm kind of maybe deep into this network. So I have n channels, and then I have a d1 by d2 size patch. If I'm going to draw weights from this model now, like my weights are going to be some tensor, and the covariance is going to be this parameterized by the square root of the covariance matrix. So I can draw my weights by drawing a matrix of IID Gaussian 0, 1 variables, and then multiplying by some matrix, which is a square root of a covariance. And just to be clear about what the shapes are in a convnet, right? So that means I'm just doing this in the usual PyTorch order. I have n out channels, and then I've got n d1, d2 other variables there. So that's the shape of G, by the way. That's the same shape as G. And then the shape of C is going to be this n times d1 times d2 squared. Okay. So that's just what I'm showing you here. It has that structure. And what we actually do, just to kind of make things clear, what's weighting channels and what's weighting space, is we factor it with a Kronecker product. Okay. And to be more specific, we parameterize the covariance square root. Okay, so that's what we're parameterizing in our model as in the Cholesky decomposition. And we have to make sure that the diagonal is positive, but not to be a square root. Okay, so we do this, and then we freeze the random part G, and then we can learn this C, right? Okay, so what does this do? Well, we put this in a bunch of just, standard models, ResNets, a V1-like model, bunch of stuff. And we looked at fixed features, we looked at learnable features. I think there's a lot going on here, but the thing to take away, maybe if you just look at these last 3 columns, okay? So this is a ResNet, or 4 columns. It's trained on CFAR and different variants of CFAR. This is just CFAR with fewer samples, small samples. And okay, so a traditional network gets 78% on CFAR, 195 on CFAR. Great. If I don't learn any of the covariance, I'm over here, not doing very well. I'm at initialization, basically. And then if I learn the covariances, I do better and better as I learn more parts of the covariance because I have more parameters to work with. This is should be obvious, but one thing that's sort of interesting is the biggest performance boost comes from learning the channels. Okay, so this column here, I learned the channel-wise covariance, and the spatial filters are just pure random filters, white noise. So most of the performance comes from learning the channel, how the channels covary. Okay. Okay, so what is this rainbow network thing? So this isn't an idea or a term that I came up with. So it's basically this deep structured random feature network, like I just told you about, but with this extra alignment step. So what's that? So this was a paper by Florentin Guth and co-authors. So they called it a rainbow network. They didn't actually tell you why it's a rainbow network. It's just this picture. So they use different colored covariances. So there's structure in the covariances, and they have them changing across layers. So it kind of looks like this rainbow. Nice name. So they do this, and then there's this alignment step that I'm not telling you about. But they were thinking about it specifically as a model of trained networks. So they take a deep network, put it through the standard pipeline, and they look at the weights, and then they try to fit a Gaussian model to them or some other covariance model. And they specifically actually were using wavelet spatial filters. And what they showed, which is pretty amazing, is that if you do this alignment step that I'm going to tell you about, that kind of deals with the fact that a new random draw of these weights is going to have different, it's not going to be equivalent to a previous random draw. They showed that you could take a traditional network, it gets 90%. This is changing width. Okay? And then they take they fit the covariance of the weights at every level just by looking at the trained network. And then they sample a new network with those covariant structure. So they sample new Gaussians. And they have this alignment trick. Just by sampling a new network and doing this alignment trick, they can still get, I don't know, 80% accuracy on this dashed line. Okay? If they're wide enough. And then if they just train the classifier head afterwards, they can bump up to like 85% accuracy. So all the training they did is just retraining the classifier in that case. So they're still doing pretty well. Yeah.
So, sorry. Can you say more exactly how these covariances are calculated?
It's a little bit complicated in this case because they just are trying to calculate the channel wise. So I think it's like for every.
They do it from weights or they do it from data?
From weights, yeah. Yeah. They treat each weight. They treat every, so they have n out, but so for every one of these indices, they have a vector here if they flatten across those last three indices, and they treat those each as random samples. Yeah. So what's this alignment thing that's kind of mysterious? Well, this was, I think, very interesting that they chose this. So the idea is that if I have a new sample, I have a new set of features that come from re-randomizing my Gaussian part. I'm going to call that phi prime. And I have another set of features from before. They're just going to solve for an orthogonal matrix that makes this distance as small as possible. So they're solving this orthogonal Procrustes problem. Okay. So they have to know what the features were before they re-randomize, by the way. Why you need to do this, right? So if these are my weights, right? And they have this structure, and then I sample a new set of weights, G prime. There's really no, there's no reason for these rows. So the columns are correlated in a certain way according to this C matrix. But the rows have there's no similarity between the rows. So they need to somehow align these rows in the channel space. And it makes the kernels the same. Okay, I'm keeping track of my time. So we tried this out, and we were working with ResNet 18. That's what I'd show you before with the structured random features. And we tried a couple different ways of aligning, and their method is called, I'm putting it AAs, because they actually align in the activation space, activation alignment in the features. Well, it kind of breaks down in ResNet 18. It doesn't work very well. The accuracy you get is garbage in ResNet 18. What we saw was that the accuracy was breaking it down, as you got deeper into the network by just kind of training readouts from earlier layers. And And they'd only really tried it up to 7-layer networks. So we kind of thought maybe this model was a bit wrong, but my student Wawas actually had a good idea, great idea. So that what they had done before was they have 2 networks with different layers, so different features, but they passed the same input in both networks. And what they did is they passed input through all these intermediate layers, and they assume in this one that we're going to align that they've aligned all the previous layers, because it's kind of a iterative process. You do it layer-wise. And what they do is, they've aligned up to layer L-1. They're trying to align layer L while they solve the problem at this stage. Okay, so the inputs pass through L layers before they have to align it. And so what we do instead is we just do it at every layer instead. So we have to keep track of the other network, but we feed an input through the 2 different layers and then align. And so we're just kind of short-circuiting the process. But it doesn't break any of the theoretical assumptions that they make about the fact that the alignment matrix only depends on earlier layers and it's orthogonal. That's all preserved. And we also, just because we thought it would be crazy to try, we didn't think it would work, but we decided to just try sampling new weights in every mini batch we do training of these things. So we're learning directly that covariance matrix C. And every mini batch, we do gradient descent on C. And now we just sample a new set of random weights. We re-randomize our Gs throughout the whole network. And we keep this one pathway, this one set of weights, kind of just fixed. So we have this one reference network that we're aligning to the whole time, but then the rest of it's changing. And the information is propagating just through the changing pathway, except the alignment kind of goes through the other one too. Okay, so yeah, here's my gratuitous skiing photo and rainbows, double rainbow. All right, so we can get it working at Resonant 18, and we're kind of reproducing that curve I showed you from the rainbow paper. And we're getting higher accuracy than they do as long as our network is wide. And we actually tried this thing too, where we ensemble the outputs of these networks. So we randomize 10 different times, keep this fixed pathway, and we can boost the performance quite a lot on this green curve. And there's 0 fine tuning happening for that green curve. So the only information that's kind of being kept about the initial network is the alignment. And we can even get it to work up to resonant 50, although at the higher widths, you can see that the accuracy goes down. So we think some kind of overfitting is going on here. And then if you look at the covariance spectra for these learned covariances, you see that they fall off like kind of you would expect. So there's some low rankedness of this, and we learned directly in a low rank parameterization of the covariance as well. And we can get fairly high accuracy, like not much drop off, even if we restrict the rank to 1/16 full rank or 1/37 full rank. So that's also sort of an interesting thing. All right, so I hope I've convinced you that random networks are more than just initialization, that we could use them maybe away from initialization if we build in some structure, and that maybe if we think about kernels in a more holistic way, where we're thinking about the kernel after learning, or as a kernel that's changing throughout learning, that maybe it has something to say about deep learning. The ensembling thing, I thought I was sort of surprised by how much better it did versus not ensembling. So we're kind of interested in going towards questions of robustness and maybe the Bayesian type neural networks or federated learning with that. So these are kind of the ongoing things that we're playing with. So thanks for your attention.
You stay on schedule, maybe one quick question? Yep.
Sorry.
I was wondering if you got an intuition about what is happening in the alignment process and why auto proceeds and not computation-based alignment.
Okay, yeah, so the question is about what's happening in alignment and why orthogonal progressivity is not permutation. Yeah, so there's this Git rebasin paper where they use permutation alignment. Yeah, I wasn't aware of that, so that's interesting, and I've heard of it now. I think the reason for orthogonal is from the kernel consideration. So we took this from Florentin's rainbow paper idea. So it has that nice property of, if you're interested in kernels of deep networks that have some structure, of that thing being well-defined under all orthogonal matrices. So yeah, I think that's the main reason. Thank you.
Yes.
While we're getting set up here, it's my pleasure to introduce the final speaker of the day and of DeepMath for the year, Ching Chu, who is a professor at ECE and part of the Data Science Institute at University of Michigan. He has founded his own conferences, CPAL, if you may have heard of it, as well as won a number of awards, including an NSF career. So we're extremely happy to have you here. Welcome, and it's all yours.
Thank you for the great introduction. So my name is Ching, I'm from University of Michigan. So today I want to talk about something I find very interesting in learning and controlling diffusion models. So first I want to start with a broad introduction of diffusion models. So in the past 10 years, right, we have witnessed the exponential growth of generative AI models, from the VE to GANs to and recently to GPT models to Sora. And if you look at the language models, right, this is start from the transformers to ChatGPT and to cloud, etc. And if you look at vision models, this is start from the VE to GAN, Flip model, and to DALI stable diffusion, and recently the Sora video diffusion models. So what is, and this talk will be focusing on diffusion models. And so what is generative models? So the basic idea of generative models is that we are trying to learn a model in a supervised fashion, that we want to learn models on raw data modalities, like images, audios, or text, etc. And then once we learn the model unsupervisedly, we input the model, so we input a noise into the model, and then we hope that we can generate some realistic data from the model, right? Either images, audios, or text. And this kind of generative model starts, around 10 years ago from this kind of original autoencoder. And the basic idea here is that we know that autoencoder is that we are doing data compression or feature learning, right? And we are basically learning an encoder and then a decoder. But later on, people find that actually you can use decoder to do generation. You can input a noise into the decoder and it will generate images. But unfortunately, for a variable autoencoder, because you are doing compression and generation at the same time, so the generation quality is not so good. Later on, people introduce this kind of a GAN, generative adversarial network, right? And the basic idea here is that you are learning a generator and a discriminator, and the generator is trying to fool the discriminator, and then you are solving a minimax problem. And once you train the model, the generator will be serving as a generative model to generate close to real images. But unfortunately for GANs, although the generation quality is pretty good, the bottleneck is for the optimization, because you are solving a minimax problem. So the training is not very stable, that you cannot train again on very large scale data set. You will encounter this kind of so-called mode collapse problems. And very recently, I think in the past few years, right, we have witnessed this exponential growth of diffusion models. And the diffusion model is different from the GAN or VE-based method is that the VE and GAN method is doing one-step generation, right? It's using a neural network that you input a noise, and in one step, you will generate an image. The diffusion model is different, is that you are gradually starting from the noise, you are gradually removing the noise from through a reverse sampling process. And people like diffusion models because the training is more stable, and you can train the diffusion model on a very large data set. You don't suffer mode collapse. And also, there's many ways to control diffusion models. For example, you can use tags to image control to this kind of tag-to-image generation. You can use gradient guidance to solve inverse problems, like for this kind of gradient guidance to control the generation. And also, you can do this kind of a human-computer interaction that you can input a sketch and use this kind of sketch to control the generation of your model. And very recently, this OpenAI released this kind of a so-called Sora model, right? So they can generate realistic videos using this kind of diffusion model. So what is diffusion model? So the basic idea of diffusion model is involves two processes. So one process is it's a forward process that is kind of trivial. So it just starting from an image, and then you gradually inject noise to the image, and you break the image into a pure noise after many steps. And this can be described by a forward stochastic differential equations, something looking like this, where the F and G are given. They are predefined diffusion and drift functions, and W is the Brownian motion. And this is a continuous version of this kind of forward process. And the non-trivial part of the diffusion is this backward process. So the backward process is that you are starting from a pure noise, and people show that actually you can reverse this forward process through a deterministic ODE. But the key thing for this reversal is that you need to know the score function or the gradient of the log likelihood for every time step t, right? If you can know this oracle of the score function, you can reverse this process from a pure noise to generate images. And so then the remaining question is that, okay, we can reverse this process, but how can we know the score function, right? The score function is something that we not know ahead of time. And idea here is that we know that neural network is a universal approximator. Then maybe a good idea is that we use a overparameterized very large neural network to approximate the score function for every time steps. And if you look at the stable diffusion or the initial work of diffusion models, people are using UNet to approximate this score function. And more recently, people are using transformers, this kind of a UVIT or DIT models to approximate the score function. And the reason people are going to this kind of transformer-based models is because transformer models satisfy the scaling law better. And also it enables a multi-model cross attention generation. And so, okay, so we can use, so we know that we can approximate the score function using a neural network, but the question is that how can we learn the score function? And typically this is done through score matching, that you are matching the score with the neural network, right? Minimizing this kind of loss in expectation. However, because we don't know the score function, right? This loss function is intractable. But people show that because the noise is Gaussian, you can show that actually through Tweedy's formula, this is equivalent as using a neural network to predict the noise. And although this is a loss in population, but you can use, when you train a neural network, you will use empirical loss to minimize to learn the score function. So this is all about the diffusion models. So in this talk, I will try to answer two fundamental questions. So one question is about generalizability. So the question is that the diffusion model is trained on finite number of samples, right? But in practice, diffusion models can generate novel, like new contents that are very different from the training data. So the question is, first question is about generalizability. So why and when diffusion model can generate new samples that are different from the training data set? So the second question is about controlling diffusion models. How can we control or manipulate the content generation of diffusion models? And my argument here to enable this is that actually both the data and the model actually can be approximated by a union of low-dimensional subspaces, and this will be enabling generalizability and controllability that I will talk about in the next several sections of my talk. So first, to understand generalizability and controllability, I want to start with an interesting phenomenon that we find in diffusion models, which is, we call this reproducibility phenomenon in diffusion models. To start introducing this phenomenon, I want to start a question. Maybe Renee knows the answer, but I will introduce this question again. Is that, so suppose you train two different diffusion models on the same data set. See this S theta 1 and S theta 2, they are like U-Net and transformers. And then you train the model on the same training data set. Once the model are trained, you start from the same noise using the same ODE sampler to generate two images. So my question is that what's the relationship between the generated images between S theta 1 and S theta 2? Yeah, they are actually very similar to each other. So exactly, so this is a current model reproducibility, is that when you're starting from the same noise, actually diffusion models will be generating very close, very similar images. Even the model parameter or the network architecture is very different. So say if you use U-Net and you use a transformer, actually they will generate very similar images. And this is a visualization of a different type of question. Yes.
So, but I guess you have to control like for maybe the same size, the same same like optimization method.
Not necessary. Actually, you can use different training laws. This is also true.
Even what if there are different sizes then?
Even different size, you still have this phenomenon. As long as there's enough training, there's a certain portion of a ratio between model capacity and the training data set, which I will show later. Yes.
I assume this is pretty sensitive though to the training data being the same.
Actually, not necessary. So I will show actually there's a complementary result on this.
Seeds are
The seed, the noise seed is the same. We're using starting from the same noise to generate the image. The seed also doesn't matter much. You mean the initialization for the weight? No, it doesn't matter that much. So this is a visualization. Actually, if you look at this is each index is the same noise, and then you visually compare the images, right? They are generated very similar images for different models, like whether U-Net, transformer, or using consistent training, different losses. You will see that actually the generated images conceptually they are similar to each other. But this is only visual general measurement, right? So the question is, can we quantify this reproducibility or the similarity of two different diffusion models? And actually here we are introducing a metric to measure the similarity between two different diffusion models to quantify the model reproducibility. And here what we define model reproducibility is that say we have two different diffusion models, generate two images, X1 and X2, and we using some neural network to map the generated images into a latent space to get rid of some scaling or color difference issues. And then we measure the reproducibility between the similarity between two samples through the cosine similarity, right? And this network usually is trained using an unsupervised learning fashion, like contrastive learning, or you can use even larger network like Dino V2 or something like this to embed your sample. And we define a reproducibility score, where reproducibility score is a probability measure, where we set a very strict, quite large threshold. So when the similarity is high, so then we see that there's a model reproducibility. And this reproducibility score actually is empirically measured on a lot of samples, like 10,000, for example. Yes.
I'm sorry, I just didn't catch exactly how this speech is trained.
Oh, so this is an unsupervised trained neural network. Okay. You can use like any contrastive learning neural network, or you can use like this kind of open source Dino V2 from Meta. Yeah. And this is a similarity matrix, right? And you can see that actually, if you compare different training architectures, training laws, sampling procedures, right, they are very similar to each other. I mean, the lowest score is 1.7, actually still pretty high. And we do an even more comprehensive study, and you can see that actually the reproducibility, the similarity is very high. So this suggests that there's a strong reproducibility between different diffusion models. But the thing is that actually the reproducibility for generative models is pretty rare. So if you look at other type of models, except diffusion models, if you look at GAN-based models or VE-based models, if you compare the reproducibility between different architectures, there's almost zero reproducibility between each other. But for diffusion models, this is same like consistent and prevalent. Moreover, so there's a complementary work from Stephen Mallet and group at Aerosimoseli. So they also started this phenomenon on different training data sets. So here, what they do is quite complementary to us, is that we train on the same data set, but they train on non-overlapping data set, draw from the same subset from the same data set. So here, S1 and S2 are non-overlapping subset from the same data set, and N is the number of training samples. And you can see that when the number of samples is very large, you start from the same noise to generate images. Even the data sets are not overlapping, you are generating very similar images to each other. So which means the reproducibility is a very strong generalization phenomenon, right? So this is like even independent of your data set, as long as they draw from the same distributions, right? But over here in our work, we started more, take a step further. We are trying to study the reproducibility in terms of model capacity versus the training data set. So here we compare different model capacity, reproducibility between different model capacity as well as the training data sets. So here the x-axis is the size of the training data, and the y is the reproducibility score. And you can see that actually reproducibility manifests in two different regimes. So when your training data set is small, right? So you have a very strong reproducibility, and then you increase your data set, the reproducibility diminishes. And a surprising thing is that when you further increase your training data set, the reproducibility between different models reemerges again. So to interpret this, so we also need to understand, to study this relationship between generalization. So here we measure the generalization, but essentially this is like a memorization score. So basically the generalization we define is that we measure, so say if we generate a new sample X, and we measure the similarity, the dissimilarity from X across all the training data set, all the training samples, where Yi are the training samples. So if X is close to one of the training samples, then the generalization score is 0. So when X is different from all the training samples, so we say this is a generalization because it's generating a new sample different from the training data set. And if you visualize this generalization score versus the number of training data points, you see something like this. So where when the training sample is small, you have memorization, right? You are memorizing the samples. But when you increase the number of samples, you start to generate new samples. And there's a phase transition from memorization to generalization. And if you put the two curves together, you will see some trend or common structures here is that in the memorization regime, you have a very high reproducibility, but you are just memorizing the data. You are not generating any data points. And in the generalization regime, right, this reproducibility co-emerges with the generalization, right? So you have strong reproducibility and also you have a very strong generalization, and they are occurring at the same time. And also, yes.
Sorry, is it intuitive or not that on the left figure, as you increase the data set size from say 2 to the power of 7 to the power of 9, the reproducibility score decreases? Because I was imagining as you increase the, if you get more data, then the model should be better in some sense. Like,
so you mean
what's your intuition for the memorization regime?
So I think they are transiting from memorization to generalization. Actually, there's in a memorization regime, you are learning the empirical distribution, and in a generalization regime, you are learning the underlying distribution. When you're increasing the data, the model is trying to escape this kind of memorization to generalization. Actually, the curve here is not so good. I think that's the reason. Actually, there's a transition to that. Yeah. And more recently, people also argue that diffusion models are good representation learner. They can learn good representations, like they are self-supervised representation learners. And if you look at the linear probing of the representation on the diffusions, there's also a phase transition, right? So here, this is a linear probing accuracy, and you can see that the linear probing accuracy actually is from like a random guess to a very high accuracy. And this suggests actually when you learn a good distribution, you can learn good representations in diffusion models as well. So this really indicates that there's a strong generalization phenomenon happens in diffusion models, and how can we understand generalization in diffusion models? This is something that I want to talk on next from this reproducibility phenomenon. So here the question is that from this kind of reproducibility, we know that all diffusion models are learning the same score function, right? And that's why they reproduce to each other. So, but the second question, a more important question, is that so what distributions is diffusion model learning? Are they learning the empirical distribution, or are they learning the underlying distribution of our data? And so if you look at this curve, right, obviously it's suggesting that when you have small data, you are learning the empirical distribution because the model is just memorizing. And when you're increasing the data set, you are learning the underlying distribution of your data. So we can introduce this kind of empirical distribution. The empirical distribution is basically a summation of the delta function of your data set, right? And you can think about the generalization, maybe because you have enough samples, right? If your sample increases, then the empirical distribution gonna to interpolate or approximate the underlying distribution. But for empirical distribution to approximate, to well approximate the underlying distribution in high dimension, you suffer from this so-called curse of dimensionality. For example, if your empirical distribution to approximate your underlying distribution to epsilon close, so the number of samples you need actually is literally growing with your dimension, right? It doesn't seem to be possible that in high dimension you have enough sample to enable generalization. However, if you look at when diffusion model generalize, so the translation happens is much better than the worst case phenomenon, where the number of samples is actually finite. It's around 10,000 number of samples. You will be entering this kind of generalization gene. So it seems like diffusion model can learn the distribution without the curse of dimensionality, right? And why this happens? So I would argue, is this because the underlying distribution you are learning actually is very low dimensional. This can be reflected in the intrinsic structures in your model as well. Here, what we are showing here is that we are considering denoising autoencoder formulation of training diffusion models, where we are learning a diffusion DAE to directly predict the image. And this is actually equivalent, almost equivalent to score prediction through Twitty's formula. And this curve showing here is showing the rank ratio of the Jacobian for the DAE. And you can see that this is a very high noise, and this is like a clean image. And you can see that actually the Jacobian is very low rank in the intermediate time steps. And here we are plotting the rank ratio. Basically, we are showing the numerical rank of the Jacobian divided by the total dimension. And you can see that actually across different data sets, right, you can see a very consistent trend that the Jacobian is very low rank in the intermediate steps, which means there's a lot of low dimensionality in your model. And this low dimensionality in your model reflects that actually the intrinsic dimension of your data actually is pretty low. And indeed, there's a recent work from Winston group and also many other groups. They show that actually the intrinsic dimension of different data sets is very low. Even on CIFAR, like on ImageNet, so the intrinsic dimension is around 43. So I would argue is that there's a blessing of dimensionality is that the number of samples you need to enable generalization actually grows with intrinsic dimension rather than the ambient dimension. And that's why diffusion model can learn underlying distributions. So to rigorously showing this actually is very hard because the image distribution is not known and it's very, yes.
Sorry to interrupt. I was just say that once you start doing the forward process, the dimensionality like it's going to become.
Yes, we are getting closer to the image. The Jacobian is not low rank anymore.
Right.
Yeah.
Because of the running. So I guess my question is, even if the true data is low dimensional, the forward process still would not be. So
yes, so I think here this kind of rank here is capturing the intrinsic dimension, but here it's not, right? If you're getting closer to image, this is not capturing the intrinsic dimension. So for image distributions, it's very complicated. You don't know what the underlying image distribution is. So it's very hard to quantitatively study the generalization. So here, what we did is that let's consider a simple model that is simple enough that we can study the generalization. And here, what we do is that let's consider a mixture of low-rank Gaussian distribution. And the reason we consider this is because the mixture low-rank Gaussian is very simple. And we can analytically derive the optimal score functions and posterior mean estimators for the mixture Gaussian, low-rank Gaussian. So here I want to notice you is that this is a very different from this kind of mixture Gaussian assumption people studied, is that we are assuming that the covariance matrix is degenerate and it is a low rank. And basically the mixture low rank Gaussian is assuming that your data is generated from a union of subspaces. And for each subspace, the data is a Gaussian within that subspace, right? And let's study whether diffusion model can learn such a distribution well, and when and why diffusion model can learn such a distribution. And the thing, as I mentioned, is that this model is simple enough, right? You can derive the optimal posterior mean estimator. This is a closed form solution. for this mixture low-rank Gaussian. To simplify the study, let's first consider where we only have one Gaussian, where k is equal to 1. And we assume that the distribution is just one low-rank Gaussian. And let's parameterize our neural network according to the optimal posterior mean estimator. And we are learning the basis. Here, then we are essentially just learning the basis U for the mixture of Gaussian. An interesting thing we can show here is that if you do such a simple parameterization, then the training loss for this DAE actually is equivalent to a PCA problem. You can show that this actually is essentially equivalent to a PCA problem. And we know that PCA problem, right? There's a transition from learning the basis or not learning the basis, right? If your number of samples is larger than the number of the intrinsic dimension of your subspace, you can learn the basis, right? If you're smaller than the intrinsic dimension, you are not learning the basis. And this intuition can be carried to k larger than 1 case, where when k larger than 1, we assume the underlying distribution is mixture low-rank Gaussian. And if you parameterize our neural network according to the optimal score function or the posterior mean estimator, and you can show that actually this DAE training is equivalent to subspace clustering problem. And if you equivalent subspace clustering, we also know there's a phase transition depending on the number of samples, right? If your number of samples is larger than the intrinsic dimension of each subspace, you can learn the basis of each subspace, right? And this is a plot of the phase transition of PCA and the diffusion models. Actually, the phase transition is quite similar, but diffusion model is a little bit harder to learn. And this is a phase transition of subspace clustering and diffusion models. They show similar trend. And we also tried on the real network, like we trained on UNet on this kind of mixture low-rank Gaussian and the real image data set. And you can see that actually there's a phase transition from memorization to generalization to learn underlying distributions of our data. And moreover, another interesting thing we find is that if you look at the basis of the Jacobian of the DAE, actually the basis of the Jacobian have semantic meanings. So you can do this kind of manipulation of your generation through this kind of semantic subspace in your Jacobian, that each basis actually corresponding to gender, head, figure, color, etc., that you can manipulate along the dimension to manipulate your content generation. And if you just editing along an arbitrary dimension or direction, you cannot change anything in your image. But if you manipulate through the basis of your subspace, actually you can change the semantic meanings of your image. So next, I want to, based on this generalization of this kind of phenomenon, to tell you a little bit about the controllability, how to control the generation of your diffusion models.
Sorry,
yes.
Is it Jacobian with respect to theta or x?
It's with respect to x, actually. So yeah, so here, actually it's a little bit confusing, but actually it's with respect to x. Yeah. And there's an equivalence due to Tweedy's formula. So yeah, yes.
This result in 39, would it be true if sigma I was an arbitrary?
Sorry, which?
Here, so that formula E of x0 given by t. If instead you simply substitute transpose of that formula by sigma k, wouldn't the entire result sort of be true also if the sigma matrix is full rank? In a sense, is this a result for a mixture of low rank Gaussians, or is this a result of?
I think here we are assuming that this UK, they need to be orthogonal to each other. So if they are all full rank, I think there's no disentanglement between those. So
you need to prove that formula?
Oh, for this one, no, we don't.
But that's exactly what I mean. I'm trying to understand what parts of the statements depend explicitly on these being a low rank mixture with orthogonal components versus which results are just valid for a mixture of gadgets. Yeah.
Yeah, that's a good question. Yeah, I have to think about it. Maybe I need to think about this. So I think the sample complexity will be different. So here, and also, I think in the expectation, we're doing this kind of a derivation. You need some orthogonality of this kind of subspaces to derive this kind of expectation. Yeah, this is a good question. I need to go back to think about this. Yeah, sorry for that. So next, I want to talk about this controllability of your diffusion models. And actually, when you know that the bases have this kind of semantic meanings, actually you can manipulate your generation. That we introduce a method called local edit. And the basic here, I want to show you some results before I introduce methods, the high-level intuition of the methods more formally. So here we introduce a method like that we can edit or control the generation of your images through manipulating the semantic subspaces in the Jacobian. And actually, we can manipulate your image generation. Like we can do local control to control the mouth shape, the hair curvature, hair amount, and the eye shape. This kind of editing direction we find actually is quite homogeneous and transferable. That say if you can edit one image, right, you can find one semantic direction on one image, and you can transfer that direction to edit another image of similar shape. And our editing is one step. So if you edit one time step t, for example, you edit t equal to 0.5, and then you can transfer editing to another time step that you can achieve similar effects. And the more interesting is that this kind of editing direction that actually they are disentangled, that they can be composed to each other. So for example, you have an image, and then you can change your eye size through one editing direction. And then you can change another editing direction to compose the two editing directions together. And you can not only changing your eye size, but also change the smile together. And they are those editing directions are disentangled, and they can be composed. But this image showing that you are adding a smile and reducing hair color. And another interesting thing of this editing direction is that they are linear. So you control the strength of the editing direction, that you can open the mouth and close the mouth of your image. And this is we can also do this editing not only on unconditional diffusion models, but also for text to image diffusion models that we can do here up, like beard removal, like adding a glass, etc. So the question is that how can we do this? How does this kind of a local edit methods works? And here we are looking at this kind of a denoising framework. And actually, this is a very through Twitty's formula, right? This is essentially the same, approximately the same with this kind of a DAE framework. You can think of this is a DAE, right? And this is this kind of denoiser framework. And we are looking at this kind of posterior mean predictors, which is mapping from the piece noise level to the clean image. And what we are looking at is that we are looking at the first order approximation of this posterior mean predictor. And if you do a first order Taylor expansion at xt, right, you can write this your first order expansion as the posterior mean predictor at xt plus the Jacobian multiply the delta x, right? Delta x, you can think of delta x is the editing direction you are moving at. And what we find is that if you look at this Jacobian matrix, right, this Jacobian matrix is low rank at certain time steps, right? It's low rank at intermediate time steps. And also, if you look at this linear approximation, if you compare your posterior predictor with this linear approximation, you compute the norm difference, and you also compute the cosine similarity between those two, you will see that even if you choose a very large lambda, where lambda is a strength of your delta x, you will see that actually this is a pretty linear, which means that actually this function itself actually is a pretty linear function. And this linearity actually enables us to do this kind of one-step editing, is that we will be editing at a time step t that the Jacobian is very low rank. And we will have the Jacobian, because it's low rank, right? We can use a generalized power method to compute the compact SVD of the Jacobian. And then we'll be editing along one of the basis direction of the Jacobian. So basically, you are choosing your delta x as one of the singular vectors of your Jacobian matrix. And if you hit the Jacobian with a singular vector matrix, well, you can see that actually the eigenvectors is orthogonal to each other, right? So most of the terms will be canceled out. If you're editing along VI, right, you are basically editing the UI, the semantic basis, along the semantic basis UI of your image, right? And then you can change your image along the semantic basis to edit your image. And here, we utilize this kind of low rank property of your Jacobian to enable efficient computation of your efficient SVD, compact SVD of the Jacobian matrix, because it's a low rank, right? And we are choosing your time step where the Jacobian is very low rank. Yes.
So you're saying in these directions standard basis Jacobian is low rank, and they correspond to different semantic meanings.
Right.
Can you choose those semantic meanings? Like, let's say that I wanted to choose something in particular. Would I know?
No, we don't. Actually, we need to interpret afterward, because this is an unsupervised approach. So we need to interpret after we edit. Yes.
So, a priori, let's say I didn't have any low rankness. This Jacobian edit could be done at any layer, because
yes,
for every layer I can PCA.
Yeah, so we show this basically.
But just finish with the question. So evidently, for t is equal to 0,
right?
PCA is a valid model only for a few classes of images, like faces and they're very light.
Right.
So what? So therefore, this shouldn't be done at every t. It should be done at some t. So
right.
Why choosing the t at which the Jacobian is low rank is the right strategy?
I think why is because of the efficiency. Because the Jacobian is low rank, then you can compute the similarity computation.
My question is not about efficiency; it's more about the geometry. Like the argument is that there exists one of the representations x t where linearity, where the images are the image manifold is linear.
Yes.
And disentangling.
Yes.
That's what needs to happen. So my question is exactly why does there exist a t with these two properties?
We empirically show this, but hypothetically, yeah, I don't know exactly.
And just to be clear, the edit then is that you edit only that t, but the rest of the diffusion one is you.
Yes. You only add along this specific t. And I think that because for low rank case, right, it's more corresponding to the intrinsic dimension of the image. And in that time steps, the PCA is more meaningful. And also we are thinking that whether, this kind of Jacobian is calculated on individual images. So we're also thinking that whether we can build a dictionary at the time steps to capture all these kind of common structures across all different like images. Maybe that's will be more like meaningful. Yeah. So this is a more details of the approach I want to escape here. So basically, we can also do some local editing by doing some complementary projection. This is some high level, like more technical things I want to escape. And actually, we can visualize editing directions. And we can see that actually the editing direction indeed corresponding to some semantic meanings of the part of the species or the portion of the animals in your image. And this is a comparison of our approach, right? If you compare all this kind of existing editing approach for diffusion models, right? They either significantly changes your image or they are overdoing it and or they don't change anything of your image. And here our approach is more natural, and we can do a natural change without changing the global structures of your images, but just changing the specific target we are changing here. We are adding a red lipstick on the face, right? And then our approach seems to be more natural. Something I want to conclude here with ongoing work that we just archived recently is that this editing idea actually can be also applied to watermarking your images. So, and the idea here for watermarking, I mean, here, let me just introduce some previous approach for watermarking, right? So watermarking is about that we have so many like generated images from this kind of generated AI models, right? And we want to do this kind of a copyright protection, right? We want to identify whether these images are like protect the copyright. And there's a very famous like existing approach called this kind of tree-ring watermark. And the idea here for diffusion model using this tree-ring watermarks is that at the initial given noise, right, you are doing a Fourier transform to transform the noise into the Fourier domain. And then you do a watermark in the low frequency component of your noise, and then you generate the image. But if you look at the generation, right, because the reproducibility, and you start the same noise, you manipulate the noise in the initial noise, the low frequency component of initial noise, you are significantly changing your image when you're doing this watermarking of your images. And here we introduce a new approach which is called shallow diffuse. And the watermark you injecting here is more robust and more importantly, more invisible. And instead of injecting your watermark at the initial noise, we are injecting this watermark at the intermediate steps. And we are injecting a watermark in the high frequency component once you do this kind of Fourier transform. And the basic idea here is that remember the rank curve here, right? So the rank curve means the Jacobian is a pretty low rank in the intermediate step. And so because it's low rank, so they have a very large null space. We can inject the noise, the watermark into the null space. And this is the basic idea. And our basic idea here is that we will be injecting this delta x into the null space of the Jacobian. And then because the delta x is in the null space, and actually it doesn't change your image a lot. And that's why if you look at the watermark we injected, right, it doesn't change a lot of your images, but it can be detected because we, in practice, we are using this DDIM to implement this kind of injection, and we'll do the reverse DDIM. Actually, there's a residual part that can be detected when you are in the detecting phase of the watermark. I will skip the technical part and I will show you some results. So basically, if you do this kind of our approach, actually we preserve better the image quality, and actually it's pretty robust across different type of corruptions of your images. So to conclude my talk, so in my talk I talk about 3 parts, right? Reproducibility, generability, and controllability. And this all lies this kind of insight. There's the the data, we are using the kind of union for low dimensional subspace to approximate our data and the models. And they have semantic meanings, right? As a conclusion, right, we show that the diffusion model exhibits this kind of unique model reproducibility that they are manifest in two different regimes. One is memorization, another is generalization. And we show that actually diffusion models is very successful at learning low-dimensional distributions without curse or dimensionality. And we can control, once we know that the generalization, better understand the generalization of diffusion models, we can control the diffusion models through manipulating the subspaces to control the generation to protect the AI safety of this kind of models. So as a future work, I think there's a lot of interesting questions to be answered, right? So one of the fundamental questions is that how can we better quantify generalization, right? Especially for generative AI models, right? One important question is that we need to differentiate from memorization to generalization, right? So how can we better quantify generalization? This is a very important question for this kind of generative models. So another in practice side, right? How can we leverage kind of insight of low dimensionality for more efficient training, for better controllable generation, model editing, on learning, to increase the model interpretability and safety is a very fundamental question. Finally, this is all the references of this talk that is published in SML and NIPS this year. And there are some archive work that pending submission under review. Finally, I want to thank all my collaborators and my students on this line of work. Thank you all for attendance. Thank you.
Any questions?
Yes, sir.
When the Jacobian of the flow is low rank, you expect the flow to be stiff, very stiff. So do you see any numerical problems with the stiffness in integrating the flow? When the rank of the Jacobian is low?
Sorry, can you, so what do you mean, Steve?
When the rank of the Jacobian is low, the flow also will be very stiff. So you should have difficulty integrating. And I'm wondering whether you see this.
I think this is approximately low rank. So here we compute the numerical rank. But actually this is not exactly low rank.
Oh.
Yeah, so there's some tail on the singular values.
I see.
Yeah. Yep.
I was just asking. Can you comment at all on the character of these like unions of subspaces that are learned in this approach? And what I mean by character is like the like what is their dimension? Do they intersect? And why? I guess like just in particular with the intersection question.
We assume very simple model. We assume that all the unions, the subspaces are orthogonal to each other.
Okay.
Yeah.
So
but I think the next step is how we consider the angles between different subspaces and capture the sample complexity. We haven't done that because the orthogonality simplifies a lot of things.
Right. Yes. And so then also I was just perhaps this is a very simple thing that I just missed, but like with the Jacobian being low rank, it's actually somewhat counterintuitive that this would correspond to this sort of union of subspaces, because I guess like if you
yes, exactly. So so in our parameterization, right? If you look at our parameterization, is exactly low rank, right? So actually if you look at this curve of our parameterization, so the rank will be always stay here, right? And I think there's some difference between our parameterization and the practical neural network. So practical neural network will be a little bit over parameterized, and there will be like a nonlinear. They have this kind of a nonlinearity there, and the phenomenon is different. I think how to close a gap between this kind of exact parameterization and the practical neural network is something that I think this is a future step to work on. And also, another thing is that if you look at our parameterization, right, our parameterization can only understand generalization or to interpret why diffusion model can learn the underlying distribution. But there's a memorization phase, right? So when you didn't have enough sample, your model will be memorized, but this parameterization doesn't capture memorization. So I think there's a lot of there's a big gap, still a big gap between our theory and the practice.
So I guess this is the case for PTA, which is just like if we have one low-dimensional subspace.
Yeah.
But like what would be expected is like, you know, if you have a union of many such low-dimensional
Yeah, so this will be corresponding to the subspace clustering problem.
Right.
Yeah.
Okay, and so like characterizing, I mean, the rank doesn't really apply, I guess, like as a useful perhaps characterization of like you mentioned, some dictionary learning was mentioned at some point.
Yeah, so I'm thinking, yeah, because I think inspired by René's Pace paper is that can we learn the dictionary? I mean, here we are like this Jacobian is calculated on individual images, right? So we are thinking whether we can like compute multiple images and build a concept dictionary or something to do the manipulation.
Especially, I really love your local framework. I have ratio when it goes to archive. Because in the local, you have identified this entangled concept adding to validate image in a space. But my question is kind of empirical. Essentially, let's say because you are doing image editing, so how do you really map a source image to the latent space that you want in diffusion? So you can impose your disentangled.
So we are doing this DDM. We are using DDM to do DDM inversion to the XT, and then we'll do the DDM and back to the image space.
I see. So essentially, in the forward process, you are using a score predict
Yeah.
forward score.
Yeah.
Code it into the latent space you want.
Right. Yes.
The directions along which you edit are singular vectors of the Jacobian, right?
Yes.
And
Singular vectors, yeah.
Yeah, and these are computed per image. How is there like a consistency across images?
Yes, I think we showed in this figure is that if you look at this, so here this figure is that we are finding one direction to edit the shape of the image, of your eyes, and then actually you can transfer to another image, and you can also edit the eyes of the. I think there's some common structures if your image look very similar to each other. Yeah, but if the images are very different, I don't think we can do this.
Did you give eyes to the tree or does it
I
just
don't
hold
think
the
so.
null space?
I don't know. Yeah. Yes, Aaron.
Can you go back to the slide with Jacobian XT?
This one or
the one with Jacobian?
This.
With the edit with the Jacobian.
Oh, okay.
J of X.
Here.
So my questions are really about just clarification. So the F of XT is the mapping from XT to X0.
Right.
And that mapping is the mapping that you learned by training a diffusion model that is just, you just took a diffusion model, computed the Jacobian, and did the edits? Or is this F the one that you train with a specialized structure that is a mixture of the
So this is a real neural network.
It's a real neural network.
Yeah.
So therefore, what you're saying is that you're just observing experimentally that Jacobian has lower rank at some intermediate.
Yes, and linearity.
And so then the question is, why does that happen? Why do you think that there exists an intermediate T? And I would imagine you're conjecturing that this is true for many diffusion models on many data.
Yes.
So
I think
why,
this also might correlate to this kind of so-called linear hypothesis, representation hypothesis in large language models that people find in some intermediate steps, representation is pretty linear. I think from Chicago, Chicago. Yeah, so we cannot like theoretically prove this, but this is like a more empirical observation. Yeah, I think there's might be some common structure between language models, LLMs and diffusion, that they also have this kind of linearity there.
Do you know what local means in Spanish?
Local, I don't know.
You should have known before you titled it.
Sorry, I don't know this. Sorry.
It means crazy.
Means crazy. So you're doing crazy edits.
Okay.
Maybe we'll do the last two.
Yeah, so how do you think that the variance of this estimate factor is? Because for the t that you pick, let's say like 0.7, the estimate, like the 2D estimate itself will be very noisy, right? The variance will be very high. So I'm just wondering, like the image itself that you might generate as your predicted posterior mean will be a very low quality.
So in practice, we are not using this posterior mean 2D formula. We are using DDM to do this. So this is done through like the DDM, like this DDM inversion to XT, and then we do this edit, and then we'll be mapped back through DDM. The general quality.
0t that you have below is from.
No, this is the image we want to edit. This is the original image, and then we'll do DDM inversion to XT, and then we do this editing, and then we'll be using DDM to map back to the clean image, and the generated quality will be pretty high. Yeah. So here the 2D formula is just to build some intuitions. Yeah.
So what determines the number of data that you need? So you said that you can call models.
So here we are using I mean for the theory we are using an exact parameterization, and I think in practice there's the generalization will be depending on the ratio between your model capacity and your training data set. I think you need a certain ratio. If your model is too large and your set is too small, then you will memorize. Right? I think there's a ratio there to capture this generalization. Yeah.
One last one.
Yeah, just curious. There is a paper from January called where they argue that like certain machine models are just like they just memorize, which sounds like it's like I guess arguing for the first regime that you showed. I'm just wondering if there's some.
I think the reason there is because they are considering a worst case. Here we are considering like this kind of mixture of low and Gaussian, right? This is not the worst case. It's more like a typical, like average case, right? If you consider like a sparse recovery, right? If your signal is sparse, you have the hope, you have finite sample to recover it. But for arbitrary case, that you cannot, right? I think that they are considered the worst case, and then you need the exponential many samples to learn the distribution. Yeah. I think the idea here is that you need to consider typical case. And typical case is usually be much better than the worst case.
All right. Yeah. Well, let's. Thank you. All right. So just to finish us off, I would like to let's see. Yep. Jeremiah has been taking amazing pictures. We'll post some online for people to get. So if you want to see your face at the poster session, Renee. So thank you all for coming. This is conference is really based around people like you coming and attending, and we'd like to thank our sponsors, ONR, Ideas, and Minds up at Hopkins, down at Hopkins. Thank you again to all of our wonderful speakers, our invited speakers. The talks will be posted on YouTube once we've processed them. They've all been recorded. Thank you especially to the wonderful support team that has made this all possible. This has been by far the smoothest AV ride I've ever been on. So thank you to Sonia for really doing a huge amount of work in getting everything organized. Pension for all the wonderful setting up of the AV and making sure we're all running smoothly. The AV team, the army of volunteers from here. I made sure to get everyone in there, so you're there. And especially thank you to all of you for the contributed talks and posters and bringing all of your new and upcoming ideas so that we can all share and learn from you. Next year, we're still planning. Stay tuned. We'll be posting on the DeepMath conference website when dates and locations and everything are established. And so, yeah, we'll hopefully see you all again. Thank you all, and safe travels back home.
Please help us by taking some of the rest of the food. Thank you.